Neutrons are not only important for the stability of atomic nuclei, but they also play a significant role in the creation of elements. In a process known as neutron capture, a nucleus absorbs a neutron, becoming a heavier isotope. This can lead to the creation of new elements, a process that occurs naturally in stars and is also used in laboratories to create synthetic elements. In terms of their behavior, neutrons are fascinating particles. They are fermions, which means they follow Fermi-Dirac statistics and have half-integer spin. This spin property is crucial in the formation of atomic nuclei, as it allows neutrons and protons to occupy different quantum states within the nucleus, thus contributing to its stability. In archaeology and paleontology, a technique known as neutron activation analysis can be used to determine the composition of ancient artifacts and fossils, providing valuable insights into their origins and histories. Lastly, in the medical field, neutron beams can be used in radiation therapy to treat certain types of cancer. The unique properties of neutrons, such as their ability to penetrate deeply into matter and their high energy, make them effective at targeting and destroying cancer cells while minimizing damage to healthy tissue. In conclusion, neutrons are much more than just neutral components of atomic nuclei. They are versatile particles with unique properties and behaviors that have far-reaching implications and applications in various scientific and technological fields. Since the dawn of human consciousness, our species has been captivated by the grandeur and mystique of the cosmos. From the earliest stargazers who mapped the celestial dance of planets and stars to the modern-day pioneers of cosmology and astrophysics, humanity has embarked on a relentless quest to unravel the enigmas that veil the universe's deepest secrets. In this cosmic odyssey, we have ventured beyond the confines of our planetary home, probing the depths of space and time, and pushing the boundaries of our understanding of the fundamental laws that govern existence itself. Imagine for a moment the breathtaking vista that unfolds before us as we gaze upward on a clear, starry night. The infinite tapestry of twinkling lights, each a distant sun in its own right, ignites within us a profound sense of wonder and curiosity. What lies beyond the reach of our earthly vantage point? What cosmic dramas unfold in the vast expanses of the universe? These questions, etched into the fabric of human inquiry, have driven generations of explorers, thinkers, and visionaries to embark on a relentless pursuit of cosmic understanding. To truly comprehend the grandeur and complexity of the cosmos, we must first grasp the fundamental concepts that form the bedrock of our modern cosmological understanding. At the heart of this understanding lies the Big Bang theory, a cornerstone of modern cosmology that describes the origin and evolution of the entire universe. According to this theory, the universe as we know it began in an unfathomably hot and dense singularity, a point of infinite density and temperature, approximately 13.8 billion years ago. In a fraction of a second, this singularity underwent a colossal expansion, known as the Big Bang, giving birth to space, time, and the primordial building blocks of matter and energy. As the universe cooled and expanded, the fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, emerged, shaping the intricate dance of subatomic particles and governing the behavior of matter and energy on cosmic scales. This early universe was a seething cauldron of energy, where the first elementary particles and light elements were forged in the intense heat of the initial expansion. Over billions of years, the universe continued to expand and evolve, with the primordial matter coalescing into the first stars and galaxies, forming the intricate cosmic tapestry we observe today. This grand narrative of cosmic evolution, from the initial singularity to the present-day universe, is a testament to the profound insights we have gleaned from observational astronomy, theoretical physics, and the relentless pursuit of scientific inquiry. The journey towards unraveling the mysteries of the cosmos has been a long and arduous one, marked by groundbreaking discoveries, paradigm shifts, and the constant refinement of our understanding. From the earliest astronomical observations of the ancient civilizations to the revolutionary theories of modern physics, each step has unveiled new layers of complexity and raised new questions about the nature of the universe. One of the most significant milestones in this cosmic odyssey was the development of the theory of general relativity by Albert Einstein in the early 20th century. This groundbreaking theory revolutionized our understanding of gravity, describing it as a curvature in the fabric of space-time itself, caused by the presence of mass and energy. Einstein's equations not only provided a deeper insight into the behavior of gravity on a cosmic scale, but also laid the foundation for our comprehension of the evolution of the universe and the existence of enigmatic entities such as black holes. Another pivotal development in cosmology was the discovery of the cosmic microwave background CMB radiation in 1964. This faint, ubiquitous glow, permeating the entire universe, is a relic of the Big Bang itself, providing direct evidence for the initial hot and dense state of the early universe. The study of the CMB has enabled cosmologists to map the primordial fluctuations in the density of matter and energy, shedding light on the formation of the first galaxies and the large-scale structure of the cosmos. As our observational capabilities and theoretical frameworks advanced, new frontiers emerged, unveiling the existence of invisible components that dominate the mass-energy budget of the universe. The discovery of dark matter, an enigmatic substance that exerts gravitational influence but does not interact with electromagnetic radiation, challenged our understanding of the fundamental constituents of the cosmos. Similarly, the revelation of dark energy, a mysterious force driving the accelerated expansion of the universe, further deepened the enigma surrounding the nature of spacetime and the fate of the cosmos. The anthropic principle and its various interpretations have led to profound philosophical implications, prompting a re-evaluation of humanity's place in the cosmos. These implications range from questioning the significance of human existence to pondering the nature of reality and the potential for extraterrestrial life. The teleological argument and intelligent design. One of the philosophical implications of the strong anthropic principle, SAP, is its connection to the teleological argument for the existence of God. The teleological argument posits that the complexity and order of the universe suggest a purpose or design, which in turn implies the existence of an intelligent designer. The SAP, with its assertion that the universe must have properties that allow for the emergence of intelligent life, can be seen as a contemporary version of the teleological argument. Intelligent design, a controversial concept that posits certain features of the universe and living organisms are best explained by an intelligent cause rather than natural processes, has also been associated with the anthropic principle. Proponents of intelligent design argue that the fine-tuning of the universe's fundamental constants and quantities provides evidence of a designer. However, critics contend that invoking a designer to explain fine-tuning is a form of the God of the gaps fallacy, which attributes unexplained phenomena to divine intervention. The problem of evil and the anthropic principle. The problem of evil, a philosophical challenge to the existence of an all-powerful, all-knowing, and benevolent God, can be reconsidered in light of the anthropic principle. The problem of evil argues that the presence of suffering and evil in the world is incompatible with the existence of such a deity. However, some philosophers have suggested that the anthropic principle may offer a response to this challenge. They argue that the fine-tuning of the universe for intelligent life might necessitate certain forms of suffering or natural evils, such as earthquakes or diseases, as byproducts of the universe's laws. In this view, the universe's fine-tuning could be seen as a justification for the existence of evil, as it allows for the emergence of intelligent life capable of experiencing moral and spiritual growth. This perspective, however, remains highly controversial, and debated within philosophical circles. The cosmological perspective shift. The anthropic principle has also led to a shift in our cosmological perspective, moving away from the Copernican principle and the mediocrity principle, which posit that Earth and humanity hold no special or unique position in the universe. The fine-tuning of the universe's fundamental constants and quantities, as well as the potential rarity of intelligent life, suggests that our existence may be unique or special in some way. This cosmological perspective shift challenges our assumptions about the nature of reality and the role of human consciousness. It raises questions about the significance of human existence, the potential for extraterrestrial life, and the ultimate fate of the universe. This new perspective encourages a sense of humility and awe as we grapple with the profound implications of our place in the cosmos. The ethical implications of the anthropic principle. The anthropic principle also has ethical implications, particularly concerning our responsibility to preserve and protect life on Earth. If the universe is finely tuned for the emergence of intelligent life, and if such life is rare or unique, then the preservation of Earth's biosphere becomes a moral imperative. This responsibility extends to future generations and potential extraterrestrial life forms as we strive to ensure the continuation of life and the exploration of the cosmos. Additionally, the anthropic principle raises questions about the ethics of space exploration and colonization. If intelligent life is rare or unique, then the discovery of extraterrestrial life would carry immense ethical implications, as we would be faced with the responsibility to protect and preserve such life. The anthropic principle thus serves as a reminder of our ethical duties as the stewards of life in the universe. The epistemological challenge. The anthropic principle presents an epistemological challenge as it raises questions about the limits of human knowledge and understanding. The principle suggests that our existence as observers within the universe might impose fundamental limitations on our ability to comprehend the universe's true nature. This idea has been explored in the context of quantum mechanics, where the act of observation is thought to play a crucial role in determining the outcome of certain experiments. The anthropic principle also challenges our assumptions about the nature of scientific inquiry, as it raises questions about the testability and falsifiability of certain theories. Critics argue that the anthropic principle is not a scientific principle, but rather a philosophical or theological one, as it is not testable or falsifiable. This debate highlights the tension between scientific and philosophical approaches to understanding the universe and our place within it. In conclusion, the anthropic principle has far-reaching philosophical implications that challenge our understanding of the universe, the nature of reality, and our place within the cosmos. From questioning the significance of human existence to pondering the potential for extraterrestrial life, the anthropic principle encourages us to confront the profound questions that arise from our unique position as intelligent observers in a finely tuned universe. This reevaluation of our cosmic role invites a sense of humility, awe, and ethical responsibility, as we strive to understand the deeper meaning and purpose of our existence in the vast expanse of the cosmos. In our relentless pursuit of cosmic understanding, we have pushed the boundaries of our knowledge to unprecedented limits, unveiling a universe that defies our conventional notions of reality and challenges the very foundations of our existence. The modern cosmological paradigm, shaped by cutting-edge observational data and theoretical insights, presents a breathtakingly vast and complex tapestry of phenomena that stretch the limits of our imagination. At the heart of this paradigm lies the notion of an expanding universe, a concept that was once met with skepticism, but has now become a cornerstone of our cosmological understanding. The observed redshift of light from distant galaxies, coupled with the discovery of the CMB radiation and the precise measurements of the cosmic background radiation, have provided overwhelming evidence for a universe that is not only expanding but has been doing so since the initial moments of the Big Bang. However, the true nature of this expansion and the ultimate fate of the universe remain shrouded in mystery. Will the universe continue to expand indefinitely, leading to a cold and lonely demise known as the Big Freeze? Or will the relentless pull of gravity ultimately overcome the expansive force, triggering a cosmic implosion and a potential cyclical rebirth of the universe in a big crunch or big bounce? The enigmas of dark matter and dark energy further complicate our understanding of the cosmos, as these invisible components appear to dominate the mass energy budget of the universe. Dark matter, whose existence was first inferred from its gravitational effects on the motion of galaxies and the large-scale structure of the cosmos, remains elusive, evading direct detection and challenging our current theories of particle physics. Similarly, the nature of dark energy, the mysterious force accelerating the expansion of the universe, continues to perplex cosmologists and theoretical physicists alike. Is it a manifestation of Einstein's cosmological constant, a repulsive force woven into the fabric of spacetime itself, or is it a dynamic, evolving field that could potentially lead to a cataclysmic ripping apart of the cosmic fabric in a scenario known as the Big Rip? Beyond the grand tapestry of cosmic evolution and the enigmas of dark matter and dark energy, the universe harbors countless other mysteries that defy our current understanding. Black holes, those inscrutable regions of spacetime where gravity's pull becomes so intense that not even light can escape, continue to challenge our concepts of physics and raise profound questions about the nature of singularities and the potential for traversable wormholes. The quest for a unified theory that can reconcile the seemingly disparate realms of quantum mechanics and general relativity remains an elusive goal, as our current framework struggles to describe the behavior of matter and energy at the most fundamental scales. The search for extra dimensions, inspired by string theory and other theoretical frameworks, has opened new avenues for exploring the hidden realms of reality beyond our four-dimensional perception. Moreover, the enigma of consciousness and its apparent connection to the fabric of the cosmos raises profound philosophical and existential questions. Is consciousness an emergent property of complex physical systems, or is it a fundamental aspect of the universe itself, woven into the very fabric of reality? These questions, at the intersection of science, philosophy, and spirituality, challenge us to redefine our place in the cosmos and our understanding of the nature of existence. As we stand at the precipice of a new era in cosmological exploration, the mysteries of the universe continue to beckon us, inviting us to push the boundaries of our knowledge and venture into uncharted realms. The future of cosmology holds immense promise with the advent of powerful observational tools, such as the James Webb Space Telescope and the next generation of ground-based telescopes, poised to unveil new insights into the formation and evolution of galaxies, the nature of dark matter and dark energy, and the elusive traces of the first stars and black holes. Moreover, the rapid advancement of computational power and the emergence of quantum computing hold the potential to revolutionize our ability to model and simulate the complex phenomena that govern the cosmos. By harnessing the power of these cutting-edge technologies, we may be able to probe the realms of the quantum and the cosmic with unprecedented accuracy, shedding light on the fundamental nature of spacetime and the intricate interplay between matter, energy, and the fundamental forces. As we continue to unravel the mysteries of the cosmos, we must also embrace the philosophical and ethical implications of our discoveries. The insights gleaned from cosmology challenge us to redefine our place in the universe and confront profound existential questions about the nature of reality, the origin of life, and the potential for extraterrestrial intelligence. Furthermore, our understanding of the cosmic tapestry compels us to consider the ethical dimensions of our explorations and the responsible stewardship of our planet and its resources. As we venture into the unknown, we must navigate the delicate balance between scientific curiosity and the preservation of our cosmic home, ensuring that our quest for knowledge does not come at the cost of the fragile ecosystems that sustain life on Earth. In this grand cosmic odyssey, the intersection of science and faith, reason and spirituality, presents both challenges and opportunities for dialogue and mutual understanding. As we unravel the mysteries of the universe, we are confronted with the profound awe and wonder that has inspired generations of philosophers, poets, and mystics, reminding us of the intrinsic connection between our pursuit of knowledge and the deeper questions of meaning and purpose. Ultimately, the story of unraveling the mysteries of the cosmos is a tale of human resilience, intellectual curiosity, and the unquenchable thirst for understanding the nature of existence itself. It is a journey that has spanned millennia, transcending cultural boundaries and uniting humanity in a shared pursuit of cosmic understanding. As we gaze upward towards the infinite tapestry of stars and galaxies, let us embrace the profound privilege of being the universe's conscious explorers, witnessing the grandeur of creation and contributing to the ever-expanding tapestry of human knowledge. For in this cosmic odyssey, we are not mere spectators, but active participants in the unfolding drama of the universe, shaping our collective destiny with every insight, every discovery, and every step towards unveiling the enigmas that lie beyond the veil of our current understanding. Imagine for a moment the sheer grandeur and awe-inspiring nature of this cosmic overture. Envision a reality where the entire expanse of space-time, the fabric that weaves together the tapestry of existence, was once condensed into an infinitesimal point of unfathomable density and temperature. This primordial singularity, a state so extreme that our current laws of physics break down, set the stage for the most extraordinary event in the history of the cosmos, the birth of the universe itself. From this infinitesimal seed, a colossal explosion of unimaginable proportions erupted, unleashing the fundamental forces of nature and giving rise to the earliest building blocks of matter and energy. In a fraction of a second, the universe underwent an incredible expansion, rapidly inflating from an infinitesimal speck to a vast, ever-expanding domain that would eventually harbor the countless galaxies, stars, and celestial wonders that adorn the cosmic tapestry we observe today. Stream. To truly grasp the profound implications of the Big Bang theory, we must first delve into the fundamental concepts and principles that underpin this monumental cosmological paradigm. At its core, the Big Bang theory is a robust scientific model that describes the origin, evolution, and ultimate fate of the entire universe, weaving together threads from various branches of physics, including general relativity, quantum mechanics, and particle physics. The theory postulates that the universe began in an incredibly hot and dense state, a cosmic singularity where the laws of physics as we know them break down. In this initial state, all matter and energy were condensed into an infinitesimal point, with temperatures and densities so extreme that our current understanding of physics cannot fully describe them. Approximately 13.8 billion years ago, this primordial singularity underwent a colossal expansion known as the Big Bang, unleashing the fundamental forces of nature and giving birth to the earliest building blocks of matter and energy. In the first fractions of a second after the Big Bang, the universe underwent a period of rapid inflation, expanding exponentially and cooling rapidly. As the universe cooled and expanded, the fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, emerged from a single unified force, separating and shaping the behavior of matter and energy on cosmic scales. During this early phase, known as the Big Bang nucleosynthesis, the first light elements, such as hydrogen, helium, and traces of lithium, were formed as the universe cooled sufficiently for protons and neutrons to combine into atomic nuclei. The journey towards the formulation and acceptance of the Big Bang theory was a long and arduous one, marked by groundbreaking discoveries, paradigm shifts, and the relentless pursuit of scientific understanding. The seeds of this cosmological paradigm were sown in the early 20th century, when pioneering astronomers and physicists began to grapple with the enigmatic nature of the universe and its origins. One of the key milestones in this journey was the discovery of the cosmic microwave background (CMB) radiation by Arno Penzias and Robert Wilson in 1964. This faint, ubiquitous glow, permeating the entire observable universe, was the first observational evidence in support of the Big Bang theory. The CMB radiation is a relic of the intense heat and radiation that filled the early universe, providing a glimpse into the primordial conditions that existed shortly after the Big Bang. Another pivotal development in the formulation of the Big Bang theory was the work of Georges Lemaitre, a Belgian priest and cosmologist who, in 1927, proposed the idea of an expanding universe based on his interpretation of Albert Einstein's theory of general relativity. Lemaitre's bold hypothesis, which challenged the then prevailing notion of a static universe, laid the foundation for our modern understanding of cosmic expansion. As observational astronomy advanced, further evidence emerged to support the Big Bang theory. The discovery of the redshift of distant galaxies by Edwin Hubble in 1929 provided compelling evidence for an expanding universe, as the light from these galaxies was stretched towards longer, redder wavelengths due to the Doppler effect caused by their movement away from us. The Big Bang theory, as we understand it today, is a synthesis of observational data, theoretical insights, and mathematical models that paint a comprehensive picture of the universe's origin, evolution, and ultimate fate. This robust cosmological paradigm has withstood rigorous scientific scrutiny and has been bolstered by a wealth of observational evidence, making it one of the most well-supported theories in the annals of modern science. At the heart of the Big Bang theory lies the concept of cosmic expansion, a fundamental principle that governs the behavior of the universe on the grandest of scales. According to this principle, the universe is not static, but rather in a state of continuous expansion, with galaxies and celestial bodies moving away from one another as the fabric of space-time itself stretches and expands. This expansion is not uniform, but rather accelerating, driven by a mysterious force known as dark energy, which accounts for approximately 68% of the total mass energy content of the universe. Dark energy, the nature of which remains an enigma, acts as a repulsive force that counteracts the attractive pole of gravity, causing the universe's expansion to accelerate over time. In addition to dark energy, the Big Bang theory also accounts for the existence of dark matter, an invisible and enigmatic substance that comprises approximately 27% of the universe's mass energy content. Dark matter, whose presence is inferred from its gravitational effects on the motion of galaxies and the large-scale structure of the cosmos, plays a crucial role in the formation and evolution of galaxies and the cosmic web of matter that spans the observable universe. The Big Bang theory also provides a compelling explanation for the observed cosmic microwave background, CMB radiation, which is a relic of the intense heat and radiation that filled the early universe. This faint, ubiquitous glow, detected across the entire observable sky, is a snapshot of the universe when it was approximately 380,000 years old, just before the formation of the first stars and galaxies. The precise measurements and analysis of the CMB radiation have revealed intricate patterns and fluctuations in its temperature and polarization, which are thought to be the seeds from which the large-scale structure of the universe emerged. These fluctuations are believed to be the imprints of quantum fluctuations that existed in the earliest moments after the Big Bang, amplified by the process of cosmic inflation, a brief period of exponential expansion that occurred mere fractions of a second after the initial singularity. Moreover, the Big Bang theory provides a robust framework for understanding the origin and abundance of the light elements that make up the observable universe. Through the process of Big Bang nucleosynthesis, which occurred within the first few minutes after the Big Bang, the first atomic nuclei were formed as the universe cooled sufficiently for protons and neutrons to combine into stable configurations. This process, governed by the laws of nuclear physics and the conditions of the early universe, resulted in the creation of the lightest elements, such as hydrogen, helium, and trace amounts of lithium. The predicted abundances of these elements, as calculated by the Big Bang theory, closely match the observed abundances in the cosmos, providing further evidence for the validity of this cosmological model. Denouement. While the Big Bang theory has emerged as the most comprehensive and well-supported model for the origin and evolution of the universe, it is important to recognize that it is not a static or immutable framework. As our observational capabilities advance and our theoretical understanding deepens, the Big Bang theory continues to evolve, adapting to new discoveries and incorporating novel insights into its explanatory power. One of the ongoing challenges faced by the Big Bang theory is the quest to reconcile it with the principles of quantum mechanics and the theories that describe the behavior of matter and energy at the most fundamental scales. The initial moments of the Big Bang, where the universe was in an incredibly hot and dense state, are governed by the realms of quantum gravity, a theoretical framework that remains elusive and the subject of intense scientific inquiry. Resolving the apparent incompatibility between general relativity, which describes the behavior of gravity on cosmic scales, and quantum mechanics, which governs the subatomic realm, is a monumental challenge that has captivated the minds of physicists and cosmologists alike. Theories such as string theory and loop quantum gravity offer promising avenues for exploring the quantum nature of gravity and potentially shedding light on the earliest moments of the Big Bang. Another area of active research and debate surrounds the nature and origin of dark matter and dark energy, the enigmatic components that dominate the mass-energy budget of the universe. While the Big Bang theory accounts for their existence and provides a framework for understanding their effects on the evolution of the cosmos, the fundamental nature of these entities remains a profound mystery. Ongoing observational campaigns, such as the study of the cosmic microwave background radiation and the mapping of the large-scale structure of the universe, aim to provide deeper insights into the properties and behavior of dark matter and dark energy. Additionally, experiments designed to detect and study these elusive components directly, such as the search for weakly interacting massive particles, WIMPs, and the investigation of the accelerated expansion of the universe, hold the promise of unveiling their true nature. Furthermore, the Big Bang theory raises profound philosophical and existential questions about the nature of the universe and our place within it. The concept of a finite, expanding universe that originated from a singularity challenges our conventional notions of space, time, and causality, prompting us to re-examine our understanding of the fundamental principles that govern reality. These questions, which lie at the intersection of science, philosophy, and spirituality, have sparked debates and dialogues that transcend the boundaries of scientific inquiry, inviting us to contemplate the deeper implications of our cosmological understanding and its potential impact on our worldviews and belief systems. As we continue to unravel the mysteries of the cosmos, the Big Bang theory stands as a towering achievement in our quest for understanding the origins and evolution of the universe. While it may not provide all the answers, it serves as a robust framework that guides our exploration and inspires us to push the boundaries of our knowledge ever further. The story of the Big Bang theory is a testament to the resilience of the human spirit, our insatiable curiosity, and our unwavering pursuit of truth. It is a cosmic overture that resonates through the ages, reminding us of the profound beauty and complexity that lies at the heart of existence itself. As we gaze up at the star-studded tapestry of the night sky, let us embrace the awe and wonder that the Big Bang theory inspires, and let it guide us on our relentless journey towards unraveling the grand tapestry of the cosmos. The Big Bang theory, while providing a robust and well-supported model for the origin and evolution of the observable universe, leaves a tantalizing question unanswered. What came before the initial singularity? This profound enigma has captivated the minds of cosmologists and theoretical physicists for decades, inspiring them to peer beyond the cosmic veil and explore the realms that precede the birth of our universe. At the heart of this inquiry lies the concept of the initial singularity, a state of infinite density and temperature where the laws of physics as we know them break down. The Big Bang theory posits that the universe emerged from this primordial singularity, but the theory itself does not offer an explanation for the origin or nature of this initial state. To truly grapple with the question of what came before the Big Bang, we must delve into the realms of quantum gravity, a theoretical framework that aims to reconcile the seemingly incompatible principles of general relativity and quantum mechanics. It is within this uncharted territory that the seeds of potential answers may lie, challenging our conventional notions of space, time, and the fundamental nature of reality itself. The quest to unravel the mysteries that precede the Big Bang has spawned a multitude of bold and innovative theories, each offering a unique perspective on the origins of our universe. These theories, born from the fertile minds of physicists and cosmologists, push the boundaries of our understanding and challenge us to reimagine the very fabric of existence. One of the earliest and most intriguing proposals is the eternal inflation hypothesis, put forth by renowned physicist Alan Guth in the 1980s. This theory suggests that the universe we observe is but a tiny fraction of a vastly larger multiverse, a landscape of infinite parallel universes, each with its own unique set of laws and properties. According to the eternal inflation hypothesis, the multiverse is in a perpetual state of expansion, driven by an intrinsic property of spacetime known as the inflaton field. This field, with its constantly fluctuating energy density, gives rise to pockets of spacetime that undergo rapid exponential expansion, forming distinct universes within the larger multiverse. Each of these universes, including our own, is essentially a bubble within the vast cosmic sea of the multiverse, with its own unique set of physical laws and initial conditions. The Big Bang that we observe, according to this hypothesis, is merely the localized event that marked the beginning of our observable universe, while countless other universes continue to emerge and expand within the larger multiverse. Another intriguing theory that attempts to shed light on the pre-Big Bang era is the cyclical universe model, which suggests that our universe is part of an endless cycle of cosmic rebirth and destruction. This model proposes that the universe we inhabit is merely the latest iteration in an infinite series of universes, each emerging from the remnants of its predecessor. According to this theory, the Big Bang that marked the beginning of our universe was not the ultimate starting point, but rather a phase transition, a transformation from the collapsed remains of a previous universe. This cyclical process is driven by the interplay between the attractive force of gravity and the repulsive force of dark energy, leading to a perpetual cycle of cosmic expansion and contraction. In this model, the initial singularity that gave birth to our universe may have been the result of a previous universe collapsing under the immense gravitational pull of its own mass, reaching a point of infinite density before rebounding and expanding anew. This cycle, according to proponents of the theory, has been repeating indefinitely, with each iteration giving rise to a unique set of physical laws and initial conditions. While the eternal inflation hypothesis and the cyclical universe model offer intriguing perspectives on the pre-Big Bang era, perhaps the most ambitious and far-reaching theory is the string theory landscape. This bold theoretical framework, which emerged from the study of quantum gravity and the search for a unified theory of all fundamental forces, presents a radically different view of the nature of reality and the origin of our universe. String theory postulates that the fundamental constituents of matter and energy are not point-like particles, but rather vibrating strings of energy existing in a higher dimensional spacetime. According to this theory, the fabric of reality is woven from these strings, whose vibrations and interactions give rise to the particles and forces we observe in the universe. However, string theory also suggests that the universe we inhabit may be just one of countless possible universes, each existing within a vast multidimensional landscape known as the string theory landscape. This landscape, which encompasses an almost infinite number of potential universes, is shaped by the intricate interplay of string vibrations, extra dimensions, and the values of fundamental constants and fields. Within this landscape, each universe represents a unique solution to the equations of string theory, with its own set of physical laws, constants, and initial conditions. The incredible diversity of this landscape arises from the fact that the extra dimensions predicted by string theory can take on a myriad of different shapes and configurations, each giving rise to a distinct universe with its own unique properties. According to the string theory landscape, the Big Bang that marked the beginning of our universe may have been the result of a spontaneous transition within this multidimensional landscape, a process akin to a phase transition in which a particular region of the landscape underwent a dramatic shift, giving rise to the initial conditions and physical laws that govern our observable universe. This transition could have been triggered by quantum fluctuations, the intrinsic instability of certain string configurations, or even the interaction between our universe and other regions of the landscape. The initial singularity that preceded our Big Bang may have been a localized event within this vast multidimensional tapestry, a seed from which our universe blossomed and continues to evolve. Perhaps one of the most intriguing and mind-bending interpretations of the pre-Big Bang era is the multiverse hypothesis, which suggests that our universe is but one of countless parallel universes, each existing within a grander cosmic tapestry. This hypothesis draws inspiration from various theoretical frameworks, including the eternal inflation model, the string theory landscape, and quantum mechanics itself. According to the multiverse interpretation, our universe emerged from a quantum fluctuation within a larger multiverse, a realm where every possible quantum state and configuration of matter and energy exists simultaneously. Each of these quantum states or configurations could give rise to a distinct universe, with its own unique set of physical laws, initial conditions, and evolutionary trajectories. In this grand cosmic tapestry, the Big Bang that birthed our universe may have been the result of a localized quantum fluctuation within the multiverse, a ripple in the fabric of existence that triggered the rapid expansion and cooling of a particular quantum state, ultimately giving rise to the universe we observe today. The multiverse hypothesis challenges our conventional notions of causality and the uniqueness of our universe, suggesting that our existence is but one of countless parallel realities, each unfolding according to its own unique set of physical principles and initial conditions. As we stand at the precipice of these bold and daring theories, it is important to acknowledge the profound implications and challenges they present. Each of these perspectives, from the eternal inflation hypothesis to the string theory landscape and the multiverse interpretation, stretches the boundaries of our conventional understanding of space, time, and the fundamental nature of reality. While these theories offer tantalizing glimpses into the realms that may have preceded the Big Bang, they also raise a myriad of philosophical and existential questions. If our universe is indeed part of a larger multiverse or a cyclical cosmic tapestry, what does this imply about the uniqueness of our existence? How do we reconcile the notion of parallel realities or infinite cycles of cosmic rebirth with our understanding of causality, consciousness, and the human experience? Furthermore, the empirical verification of these theories poses significant challenges. By their very nature, the realms that preceded the Big Bang are shrouded in the veil of the past, inaccessible to direct observation or experimentation. However, cosmologists and theoretical physicists continue to push the boundaries of scientific inquiry, exploring novel ways to test and refine these theories through indirect means. One promising avenue is the study of the cosmic microwave background (CMB) radiation, the faint remnant of the intense heat and light that permeated the early universe. By analyzing the intricate patterns and fluctuations in the CMB, researchers hope to uncover clues about the initial conditions and processes that gave rise to our universe, potentially shedding light on the pre-Big Bang era. Additionally, advances in observational astronomy, such as the detection of gravitational waves and the mapping of the large-scale structure of the universe, may provide insights into the fundamental nature of space-time and the behavior of gravity on cosmic scales, potentially offering glimpses into the realms that preceded the birth of our universe. As our theoretical frameworks and observational capabilities continue to evolve, the pursuit of understanding the pre-Big Bang era will undoubtedly remain a captivating and challenging endeavor. While the answers may remain elusive, the journey itself promises to push the boundaries of human knowledge and challenge our most fundamental assumptions about the nature of existence. Ultimately, the quest to peer beyond the cosmic veil and unravel the mysteries that precede the Big Bang is a testament to the boundless curiosity and relentless pursuit of truth that define the human spirit. As we gaze into the depths of the cosmos, we are reminded that the universe we inhabit is but a tiny fragment of a grander tapestry, woven from the threads of possibility and the echoes of cosmic evolution. Whether our universe emerged from a spontaneous quantum fluctuation within a vast multiverse, the collapse and rebirth of a cyclical cosmic cycle, or the intricate interplay of vibrating strings in a higher dimensional landscape, the pursuit of these mysteries compels us to embrace the awe and wonder that lie at the heart of scientific inquiry. As we continue to unravel the enigmas that veil the origins of our universe, let us be guided by the principles of intellectual humility and open-mindedness, for it is in the embrace of the unknown that we may find the keys to unlocking the greatest secrets of the cosmos. To truly comprehend the profound implications of the eternal inflation hypothesis, we must first delve into the fundamental concepts and principles that underpin this audacious theory. At its core, the eternal inflation hypothesis is rooted in the principles of quantum mechanics and the theory of cosmic inflation, a revolutionary idea that emerged in the 1980s to address some of the most perplexing enigmas surrounding the origin and evolution of the universe. According to the theory of cosmic inflation, in the first fractions of a second after the Big Bang, the universe underwent an incredible burst of exponential expansion, inflating from an infinitesimal speck to a vast, rapidly expanding domain. This period of rapid inflation was driven by a mysterious force field known as the inflaton field, which permeated the early universe and fueled its extraordinary growth. However, the eternal inflation hypothesis takes this concept a step further, suggesting that the inflaton field, with its constantly fluctuating energy density, gave rise to a process of eternal inflation, a never-ending cycle of cosmic expansion and the formation of new universes within a larger multiverse. In this grand cosmic tapestry, our observable universe is but a tiny bubble, a localized region within the vast expanse of the multiverse. This bubble, formed by a spontaneous quantum fluctuation in the inflaton field, underwent a period of rapid inflation, cooling and settling into the universe we observe today, with its unique set of physical laws and initial conditions. Yet the eternal inflation hypothesis posits that this process of universe formation is not a one-time event, but rather an ongoing, perpetual cycle. As the inflaton field continues to fluctuate across the vast reaches of the multiverse, new pockets of space-time undergo rapid inflation, giving rise to countless parallel universes, each with its own unique set of physical laws and properties. The roots of the eternal inflation hypothesis can be traced back to the pioneering work of physicists such as Alan Guth, Andrei Linde, and Alexander Vilenkin, who recognized the profound implications of the cosmic inflation theory and sought to explore its broader implications for the nature of the universe and the origins of reality itself. In the early 1980s, Alan Guth proposed the theory of cosmic inflation as a solution to several long-standing puzzles in cosmology, such as the flatness problem and the horizon problem. Guth's theory suggested that the universe underwent a brief period of exponential expansion in its earliest moments, driven by a hypothetical scalar field known as the inflaton. While Guth's initial model faced some challenges, it paved the way for further refinements and developments by other physicists, including Andrei Lend and Alexander Vilenkin. Lend, in particular, recognized the potential for the inflaton field to give rise to a process of eternal inflation, where quantum fluctuations in the field would continually spawn new regions of space-time undergoing rapid expansion. Vilenkin's contributions further solidified the theoretical foundations of the eternal inflation hypothesis, exploring the implications of a multiverse scenario and the potential for different regions of the multiverse to exhibit varying physical laws and properties. As the theory of eternal inflation gained traction, it began to resonate with other emerging concepts in theoretical physics, such as string theory and the anthropic principle. String theory, which proposes that the fundamental constituents of matter and energy are not point-like particles, but rather vibrating strings, also suggests the existence of a vast multiverse, with each universe representing a unique solution to the equations of string theory. The anthropic principle, on the other hand, suggests that the observable universe must possess certain properties and physical constants that are conducive to the existence of intelligent life, as we are here to observe it. The eternal inflation hypothesis provides a framework within which the vast diversity of the multiverse could give rise to a multitude of universes, each with its own set of physical laws and constants, increasing the likelihood of at least one universe being capable of supporting intelligent life. The eternal inflation hypothesis paints a breathtaking picture of a cosmos far grander and more complex than our observable universe alone. In this grand cosmic tapestry, our universe is but a mere speck, a localized region within the vast expanse of the multiverse, a realm where the process of universe formation is an ongoing perpetual cycle driven by the eternal inflation of the inflaton field. According to this audacious theory, our observable universe emerged from a spontaneous quantum fluctuation within the inflaton field, triggering a period of rapid inflation that allowed our region of spacetime to expand and cool, ultimately giving rise to the familiar universe we inhabit today. However, this process of universe formation is not a one-time event, but rather an ongoing eternal cycle. As the inflaton field continues to fluctuate across the vast reaches of the multiverse, new pockets of spacetime are continually undergoing rapid inflation, each one potentially giving rise to a distinct universe with its own unique set of physical laws, constants, and initial conditions. This incredible diversity within the multiverse arises from the fact that the quantum fluctuations that seed the formation of new universes can take on a myriad of different configurations and values, resulting in a vast array of possible outcomes. Some of these universes may be vastly different from our own, with different fundamental forces, particle compositions, and even varying numbers of spatial dimensions. Moreover, the eternal inflation hypothesis suggests that the laws of physics themselves may not be universal constants, but rather local phenomena that can vary from one region of the multiverse to another. This concept challenges our conventional understanding of the universe as a unified whole governed by a single set of immutable laws, instead presenting a reality where the very fabric of existence can take on diverse forms and manifestations. The implications of the eternal inflation hypothesis are profound and far-reaching. If true, it would mean that our observable universe is but a tiny sliver of a vastly larger reality, a mere bubble within an infinite cosmic sea of parallel universes. This perspective not only expands our understanding of the cosmos, but also raises profound philosophical and existential questions about the nature of reality and our place within it. Furthermore, the eternal inflation hypothesis offers tantalizing possibilities for resolving some of the long-standing puzzles and paradoxes that have perplexed cosmologists and theoretical physicists for decades. For instance, the apparent fine-tuning of the physical constants and initial conditions that govern our universe, which seems to be exquisitely balanced to allow for the existence of complex structures and life, could be explained by the sheer vastness of the multiverse. In a realm where countless universes exist, each with its own unique set of physical laws and constants, it becomes statistically more likely that at least one universe would possess the specific conditions required for the emergence of intelligent life as we exist to observe it. This concept, known as the anthropic principle, gains credence within the framework of the eternal inflation hypothesis, providing a potential resolution to the apparent fine-tuning of our universe. While the eternal inflation hypothesis offers a bold and captivating perspective on the origins and nature of our universe, it is important to acknowledge the significant challenges and limitations that accompany such an audacious theory. One of the primary challenges lies in the realm of empirical verification and testing. By its very nature, the concept of a vast multiverse, with each universe exhibiting its own unique set of physical laws and properties, poses significant obstacles to direct observation and experimentation. Our ability to explore and study these parallel universes is inherently limited by the constraints of our own observable universe and the limitations of our current scientific instruments and technologies. However, cosmologists and theoretical physicists continue to explore indirect methods of probing the implications of the eternal inflation hypothesis and the potential existence of a multiverse. One promising avenue is the study of the cosmic microwave background (CMB) radiation, the faint remnant of the intense heat and light that permeated the early universe. By analyzing the intricate patterns and fluctuations in the CMB, researchers hope to uncover clues about the initial conditions and processes that gave rise to our observable universe, potentially shedding light on the mechanisms of eternal inflation and the formation of parallel universes within the multiverse. Additionally, advances in observational astronomy, such as the detection of gravitational waves and the mapping of the large-scale structure of the universe, may provide insights into the fundamental nature of space-time and the behavior of gravity on cosmic scales, potentially offering glimpses into the realms that transcend the boundaries of our observable universe. Furthermore, the eternal inflation hypothesis raises profound philosophical and existential questions about the nature of reality, consciousness, and the human experience. If our universe is indeed one of countless parallel realities existing within a vast multiverse, what does this imply about the uniqueness of our existence? How do we reconcile the notion of parallel realities with our understanding of causality, free will, and the subjective experience of consciousness? These questions challenge us to redefine our perception of the cosmos and our place within it, inviting us to explore the boundaries of human knowledge and understanding. As we grapple with these profound implications, we may uncover new insights into the fundamental principles that govern existence itself, shedding light on the ultimate nature of reality and the intricate tapestry that weaves together the fabric of the multiverse. While the eternal inflation hypothesis presents a bold and audacious perspective on the origins of our universe, it is important to approach it with an open yet critical mind. Scientific theories, no matter how compelling, must be subjected to rigorous scrutiny, testing, and refinement through empirical observation and experimentation. As we continue to explore the frontiers of cosmology and theoretical physics, the eternal inflation hypothesis may undergo further revisions, refinements, or even paradigm shifts as new discoveries and insights emerge. It is the hallmark of scientific progress to embrace uncertainty, challenge our assumptions, and remain open to the possibility of revising our understanding in the face of new evidence. Ultimately, the eternal inflation hypothesis stands as a testament to the boundless curiosity and intellectual audacity that drive the human quest for knowledge. It invites us to embrace the infinite possibilities that may exist within the vast expanse of the multiverse, challenging us to redefine our perception of reality and our place within the grand cosmic tapestry. As we gaze into the depths of the cosmos, let us be reminded that the universe we inhabit may be but a tiny speck in a realm of infinite wonder and complexity. And in this grand cosmic odyssey, the eternal inflation hypothesis serves as a beacon, illuminating the path towards a deeper understanding of the origins of existence itself. At the heart of our quest to unravel the mysteries of the cosmos lies a profound enigma, the existence of two elusive and perplexing components that dominate the mass-energy budget of the universe: dark matter and dark energy. These invisible entities, which defy our conventional understanding of the cosmos, have challenged the boundaries of our knowledge and forced us to confront the vast realms of the unknown that permeate the fabric of existence. Dark matter, an unseen and enigmatic substance that exerts a gravitational pull on the visible matter in the universe, has long been a source of fascination and bewilderment for cosmologists and astrophysicists. Its presence was first inferred from the observed motion of galaxies within galactic clusters, which revealed a discrepancy between the gravitational forces at play and the visible matter present. This discrepancy, known as the missing mass problem, suggested the existence of an invisible, yet gravitationally potent, form of matter that accounted for the vast majority of the mass in these cosmic structures. Further evidence for the existence of dark matter emerged from observations of the rotational curves of spiral galaxies, which indicated that these galaxies were being held together by a far greater gravitational force than could be attributed to their visible matter alone. Dark energy, on the other hand, is an even more perplexing and enigmatic entity, responsible for the accelerated expansion of the universe, a phenomenon that defies our conventional understanding of gravity and the expected deceleration of cosmic expansion due to the attractive force of matter. This mysterious force, which appears to permeate the entire fabric of space-time itself, was first inferred from observations of distant supernovae, which revealed an unexpected dimming that could only be explained by an accelerating rate of cosmic expansion. Together, these two dark components, dark matter and dark energy, are believed to account for a staggering 95% of the total mass energy content of the universe, leaving the familiar matter that we can see and interact with as a mere 5% of the cosmic pie. The journey towards unraveling the enigmas of dark matter and dark energy has been a long and arduous one, marked by groundbreaking discoveries, ingenious theoretical models, and the relentless pursuit of scientific understanding. The seeds of these cosmic mysteries were sown in the early 20th century, when astronomers and physicists began to grapple with the discrepancies between the observed behavior of celestial bodies and the predictions of classical mechanics and general relativity. One of the earliest clues to the existence of dark matter came from the work of Swiss astronomer Fritz Zwicky in the 1930s. While studying the motions of galaxies within the Coma cluster, Zwicky noticed a peculiar phenomenon. The galaxies appeared to be moving much faster than could be accounted for by the visible matter alone, suggesting the presence of an unseen gravitational source of mass. Decades later, in the 1970s, astronomers Vera Rubin and Kent Ford made a groundbreaking discovery while studying the rotational curves of spiral galaxies. They found that the stars and gas clouds at the outer edges of these galaxies were moving at unexpectedly high velocities, defying the predictions of Newtonian gravity based solely on the visible matter present. This observation provided further evidence for the existence of an invisible gravitational component, dark matter, that extended far beyond the visible boundaries of galaxies. As observational data continued to accumulate, the case for dark matter grew stronger, leading to the development of theoretical models and simulations to explain its nature and behavior. One of the most promising candidates for dark matter emerged from particle physics, the hypothetical weakly interacting massive particles, WIMPs, which could account for the gravitational effects observed while remaining virtually invisible to electromagnetic radiation. In the realm of dark energy, the journey towards discovery began with the pioneering work of Albert Einstein himself. In his formulation of the theory of general relativity, Einstein initially introduced a cosmological constant, a repulsive force that would counteract the attractive force of gravity and maintain a static, unchanging universe. However, when observations by Edwin Hubble revealed the expansion of the universe, Einstein abandoned the cosmological constant, famously referring to it as his biggest blunder. It wasn't until the late 1990s that the concept of dark energy resurfaced, this time as a potential explanation for the accelerated expansion of the universe. Two independent teams of astronomers, the Supernova Cosmology Project and the High-Z Supernova Search Team, made a startling discovery while studying the brightness of distant supernova. These celestial explosions appeared dimmer than expected, suggesting that the expansion of the universe was not slowing down due to gravitational attraction, but rather accelerating, driven by an unknown repulsive force. This discovery shook the foundations of cosmology and ushered in a new era of exploration into the nature of this mysterious, dark energy that seems to permeate the entire cosmos. Theoretical models and hypotheses were proposed to explain this phenomenon, from a revived cosmological constant to the existence of a dynamic, time-varying field known as quintessence. As our understanding of the cosmos has deepened, the enigmas of dark matter and dark energy have taken center stage, challenging our most fundamental assumptions about the nature of the universe and the very fabric of reality itself. Dark matter, the elusive and invisible substance that exerts a gravitational pull on the visible matter in the universe, has proven to be a formidable puzzle for cosmologists and particle physicists alike. While its existence is now widely accepted, its true nature remains shrouded in mystery. One of the leading candidates for dark matter is the hypothetical weakly interacting massive particle, WIMP, a class of yet undiscovered subatomic particles that would interact with ordinary matter primarily through the weak nuclear force and gravity. These particles, if they exist, could account for the observed gravitational effects attributed to dark matter while remaining virtually invisible to electromagnetic radiation. Ongoing experiments and searches, such as the Large Hadron Collider (LHC) at CERN and various direct and indirect detection experiments, are actively hunting for evidence of WIMPs or other dark matter candidates. However, the search has proven to be a formidable challenge, as these elusive particles are expected to interact only rarely with ordinary matter, making their detection an immense technical and scientific feat. In addition to the WIMP hypothesis, other theoretical models have been proposed to explain the nature of dark matter, including modified theories of gravity that aim to account for the observed gravitational effects without invoking the existence of an invisible substance. These models, though intriguing, face significant challenges in reconciling with the wealth of observational data and our current understanding of the fundamental forces of nature. The enigma of dark energy, on the other hand, presents an even greater challenge to our comprehension of the cosmos. This mysterious force, which appears to permeate the entire fabric of space-time itself, is responsible for the accelerated expansion of the universe, a phenomenon that defies our conventional understanding of gravity and the expected deceleration of cosmic expansion due to the attractive force of matter. One of the leading hypotheses to explain dark energy is the revival of Einstein's cosmological constant, a repulsive force that was initially introduced and later discarded in the formulation of general relativity. This constant, if it exists, would represent an intrinsic property of space-time itself, acting as a constant source of repulsive energy that drives the accelerated expansion of the universe. However, the cosmological constant is not without its challenges. Its precise value, if it exists, remains a mystery, and its theoretical underpinnings within the framework of quantum field theory and particle physics remain elusive. An alternative hypothesis proposes the existence of a dynamic, time-varying field known as quintessence, which could account for the accelerated expansion of the universe, while potentially resolving some of the theoretical inconsistencies associated with the cosmological constant. This field, which could be a manifestation of a previously unknown form of energy, would evolve over time, driving the acceleration of cosmic expansion in a manner that is consistent with observational data. Despite these theoretical efforts, the true nature of dark energy remains one of the greatest mysteries in modern cosmology. Its existence challenges our fundamental understanding of gravity, space-time, and the very fabric of the universe itself, forcing us to confront the limitations of our current scientific paradigms and prompting us to explore new frontiers of theoretical and observational research. As we stand at the precipice of these profound cosmic enigmas, the quest to unravel the mysteries of dark matter and dark energy takes on a heightened sense of urgency and significance. These invisible components, which dominate the mass energy budget of the universe, hold the keys to unlocking a deeper understanding of the fundamental principles that govern the cosmos and the very nature of reality itself. While the challenges are formidable, the pursuit of these mysteries has spurred groundbreaking advances in observational astronomy, particle physics, and cosmological theory. Cutting-edge telescopes and observatories, such as the James Webb Space Telescope and the upcoming Vera C. Rubin Observatory, are poised to provide unprecedented insights into the distribution and behavior of dark matter on cosmic scales, potentially shedding light on its nature and interactions. Moreover, particle accelerators like the Large Hadron Collider at CERN and next-generation experiments are pushing the boundaries of our understanding, searching for elusive dark matter candidates, and probing the realms of particle physics that could hold the answers to these cosmic puzzles. In the realm of dark energy, ongoing observational campaigns, such as the study of distant supernova, the cosmic microwave background radiation, and the large-scale structure of the universe, aim to provide deeper insights into the properties and behavior of this mysterious force, potentially revealing clues about its fundamental nature and its role in shaping the evolution of the cosmos. Additionally, theoretical efforts to reconcile the enigmas of dark matter and dark energy with our current understanding of physics continue to push the boundaries of human knowledge. Innovative models and theories, such as modified gravity theories, quintessence fields, and extensions to the standard model of particle physics, offer tantalizing glimpses into potential avenues for resolving these cosmic mysteries. As we venture deeper into these uncharted realms, the pursuit of dark matter and dark energy will undoubtedly raise profound philosophical and existential questions about the nature of reality and our place within the cosmos. These enigmas challenge our conventional notions of matter, energy, and the fundamental forces that govern the universe, inviting us to embrace the vastness of the unknown and the limitless potential for discovery. Furthermore, the implications of unraveling these cosmic mysteries extend far beyond the realms of cosmology and theoretical physics. They hold the promise of revolutionizing our understanding of the origins, evolution, and ultimate fate of the universe, shedding light on the intricate tapestry of space-time and the fundamental building blocks of existence. As we continue to grapple with the enigmas of dark matter and dark energy, it is crucial that we approach these challenges with a spirit of intellectual humility, open-mindedness, and a willingness to challenge our most deeply held assumptions. The journey towards understanding the invisible components that dominate the universe may lead us down unexpected paths, forcing us to redefine our perception of reality and embrace new paradigms of scientific thought. Think about it. These massive particle accelerators are essentially time machines, allowing us to peer into the past and recreate the conditions that existed just moments after the Big Bang. If extra dimensions do exist, it's possible that these high-energy collisions could produce particles or phenomena that exhibit properties consistent with the existence of additional dimensions, providing the elusive evidence that we've been searching for. But the search for extra dimensions isn't limited to particle physics alone. Ongoing observational campaigns in cosmology and astrophysics, such as the study of the cosmic microwave background radiation and the mapping of the large-scale structure of the universe, could also provide indirect evidence for the existence of extra dimensions or higher dimensional theories of gravity. By probing the behavior of matter and energy on cosmic scales, these observations could uncover anomalies or deviations from our current models, potentially pointing towards the influence of hidden dimensions or new physics. Imagine the excitement of discovering subtle imprints or signatures in the cosmic microwave background radiation that could be explained by the presence of extra dimensions. It would be a monumental discovery that would reshape our understanding of the universe. But the pursuit of extra dimensions isn't just about experimental and observational efforts. It has also spurred the development of innovative theoretical frameworks and mathematical models that push the boundaries of our understanding of the universe's fundamental building blocks and the nature of spacetime itself. Theories such as brane cosmology, warped extra dimensions, and higher dimensional supergravity models offer tantalizing glimpses into the potential richness and complexity of a higher dimensional reality. These theoretical models are like maps, guiding us through the uncharted territories of extra dimensions and providing a framework for interpreting any potential experimental or observational evidence that may arise. They help us make sense of the puzzling phenomena that could emerge from the existence of hidden realms, and they offer a glimpse into the vast tapestry of possibilities that may exist beyond our current understanding. But as we venture into these uncharted realms, we must also confront the profound philosophical and existential implications that arise from the potential discovery of extra dimensions. The existence of hidden realms beyond our conventional perceptions challenges our understanding of the nature of reality and the limits of human knowledge, inviting us to redefine our place in the cosmic tapestry and embrace the vastness of the unknown. It's a humbling realization, one that forces us to confront the boundaries of our current understanding and acknowledge that there may be entire realms of existence that we have yet to uncover. It's a reminder that the universe is far grander and more complex than we can possibly imagine, and that the pursuit of knowledge is a never-ending journey filled with wonder and awe. Black holes are formed from the remnants of massive stars that have exhausted their nuclear fuel. After such a star undergoes a supernova explosion, it may leave behind a dense core that, if massive enough, succumbs to gravitational collapse, forming a black hole. The size of a black hole is defined by its Schwarzschild radius, which is directly proportional to its mass. The event horizon of a black hole is the boundary beyond which nothing can return. At the center of a black hole lies the singularity, a point where the curvature of spacetime becomes infinite and current laws of physics can no longer provide a description. Stephen Hawking proposed that black holes emit radiation due to quantum effects near the event horizon, now known as Hawking radiation. This radiation implies that black holes can eventually evaporate, leading to the information paradox. If the black hole disappears, what happens to the information it consumed? Efforts to resolve these paradoxes involve string theory and the holographic principle. String theory suggests that fundamental particles are not point-like dots, but rather oscillating strings of energy. The holographic principle proposes that all the information contained within a volume of space can be represented on the boundary of that space. Black holes challenge our understanding of the universe. They are laboratories for testing theories of gravity and quantum mechanics. The information paradox and other quantum conundrums continue to fuel theoretical advancements, pushing the boundaries of our knowledge. The future of black hole research looks promising. With technological advancements such as the Event Horizon Telescope capturing the first image of a black hole and quantum computing growing in capability, we are on the cusp of a deeper understanding. These cosmic conundrums drive the quest for a unified theory of quantum gravity, which would meld the macroscopic rules of general relativity with the microscopic laws of quantum mechanics. In conclusion, black holes are not just objects of astronomical interest. They are keys to unlocking the deeper mysteries of the universe. Every new discovery brings us closer to answering some of the most fundamental questions about the nature of reality and our place within it. Neutrons are one of the fundamental particles that make up the universe. They are a type of subatomic particle, which means they are smaller than an atom. To understand neutrons, it's helpful to first understand the structure of an atom. An atom is the basic unit of matter, and it consists of a dense central nucleus surrounded by a cloud of negatively charged particles called electrons. The nucleus itself is made up of two types of particles: protons, which have a positive charge, and neutrons, which have no charge at all. They are electrically neutral, hence the name neutron. Neutrons and protons are collectively known as nucleons, as they both reside in the atomic nucleus. The number of protons in an atom determines its element, while the number of neutrons can vary, resulting in different isotopes of the same element. Neutrons are slightly heavier than protons. They have a mass of approximately 167,493 x 10 to 27 kilograms, which is about 1.00866 times the mass of a proton. Despite their name and lack of electric charge, neutrons do have other properties, such as spin and magnetic moment, which make them interesting to physicists. Neutrons are stable within the nucleus, but outside of it, they are unstable and can decay into a proton, an electron, and an antineutrino. This process is known as beta decay. The half-life of a free neutron, the time it takes for half of a group of neutrons to decay, is about 10 minutes. Neutrons play a crucial role in nuclear reactions. For example, in a nuclear fission reaction, a neutron is fired at a heavy nucleus, causing it to split and release a large amount of energy. This is the process used in nuclear power plants and atomic bombs. In nuclear fusion, two light nuclei combine to form a heavier nucleus, also releasing energy. This process, which powers the sun and other stars, also involves neutrons. When a neutron collides with a nucleus, it can stick to it, forming a heavier isotope. This isotope can then undergo radioactive decay, releasing energy in the process. Neutrons are also used in various scientific applications. For example, neutron scattering is a technique used to study the structure and dynamics of materials. Because neutrons have no charge, they can penetrate deeply into materials without being deflected by electrons, making them ideal for studying the positions and movements of atoms within a material. Neutron activation analysis is another technique that uses neutrons to determine the composition of a material. When a neutron is absorbed by a nucleus, it can make the nucleus radioactive. By measuring the radiation emitted by the material, scientists can determine what elements it contains. Neutrons are also used in medical applications. For example, neutron beams can be used to treat certain types of cancer. Because neutrons are highly penetrating, they can be used to deliver a high dose of radiation to a tumor while sparing the surrounding healthy tissue. In conclusion, neutrons are a type of subatomic particle that reside in the nucleus of an atom. They have no electric charge, but they do have mass, spin, and a magnetic moment. Neutrons are stable within the nucleus, but decay rapidly outside of it. They play a crucial role in nuclear reactions and have various scientific and medical applications. In summary, neutrons are a fundamental type of subatomic particle that, along with protons, make up the nucleus of an atom. They are electrically neutral, slightly heavier than protons, and have properties like spin and magnetic moment. Neutrons are stable inside the nucleus, but decay outside of it. They are involved in nuclear reactions and have numerous applications in science and medicine, including nuclear power generation, nuclear medicine, and material science. Despite their neutral charge, neutrons are a vital component of the physical world, contributing to the structure and behavior of matter at its most basic level. The anthropic principle is a philosophical consideration that observations of the universe must be compatible with the conscious and sapient life that observes it. In simpler terms, it suggests that the universe's fundamental laws appear to be finely tuned to allow for the existence of life as we know it. This principle has been a subject of fascination and debate among scientists, philosophers, and thinkers alike, as it raises profound questions about our place in the cosmos and the possibility of extraterrestrial life. The anthropic principle can be further divided into two categories: the weak anthropic principle, WAP, and the strong anthropic principle, SAP. The WAP asserts that the observed values of the fundamental constants and quantities of the universe are necessary for the existence of carbon-based life. Essentially, if the universe's properties were even slightly different, life as we know it would not be possible. This idea is supported by numerous examples, such as the precise strength of the nuclear forces that allow for the formation of elements in stars and the specific value of the cosmological constant that governs the universe's expansion rate. The SAP, on the other hand, goes a step further by suggesting that the universe must have properties that allow for the emergence of intelligent life at some point in its history. This interpretation implies that the universe is, in some sense, designed for the emergence of intelligent life, which has led to criticism and controversy. Some proponents of the SAP argue that it provides a possible explanation for the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial life and the lack of contact with such civilizations. The search for extraterrestrial life has been a significant focus of scientific inquiry, with various initiatives and projects aiming to detect signs of life beyond Earth. These efforts include the Search for Extraterrestrial Intelligence, SETI, which uses radio telescopes to listen for signals from potential alien civilizations, and the study of exoplanets, which are planets that orbit stars outside our solar system. The discovery of thousands of exoplanets in recent years has bolstered hopes of finding a world capable of supporting life. One of the most intriguing aspects of the anthropic principle is its potential implications for the concept of multiple universes or the multiverse. The multiverse hypothesis suggests that our universe is just one of many, each with its own set of fields and particles, potentially governed by different fundamental constants. In this context, the anthropic principle could be seen as a natural consequence of the vast number of universes, with ours being one of the few that happen to support life. This idea is known as the anthropic landscape, which posits that the collection of universes within the multiverse contains a wide range of possible properties, and our universe is simply one that can sustain intelligent life. The anthropic principle also raises deep philosophical questions about the nature of reality and the role of human consciousness. Some interpretations of the principle suggest that the universe exists solely because it is observed by conscious beings, which brings to mind the famous thought experiment known as Schrödinger's cat. This experiment posits that a cat in a sealed box with a radioactive atom, a Geiger counter, and a vial of poison is both alive and dead until the box is opened and observed. While the connection between the anthropic principle and quantum mechanics remains a topic of debate, the idea that our observation of the universe plays a critical role in its existence is a fascinating one. The anthropic principle has also been used to explore the potential future of human civilization and the universe itself. Some scientists have suggested that the principle may provide a basis for understanding the ultimate fate of the universe, known as the final anthropic principle. This concept posits that intelligent life will continue to exist in the universe for as long as it can, and that the universe's properties are such that they allow for this perpetual existence. This idea has been used to argue for the importance of long-term thinking and the responsible stewardship of our planet and its resources. Despite its many intriguing implications, the anthropic principle remains a controversial and debated concept. Critics argue that it is not a scientific principle at all, but rather a philosophical or even theological one. They contend that the principle is not testable or falsifiable, which are essential criteria for scientific theories. Additionally, some scientists have expressed concern that the anthropic principle may be invoked as a last resort explanation for phenomena that are not yet understood, potentially stifling further inquiry and scientific progress. In conclusion, the anthropic principle is a complex and multifaceted concept that raises profound questions about the nature of the universe, the possibility of extraterrestrial life, and the role of human consciousness. While it has inspired fascinating debates and theories, it remains a subject of controversy among scientists and philosophers alike. As our understanding of the universe continues to evolve, the anthropic principle will undoubtedly remain a vital and thought-provoking part of the conversation. The anthropic principle is a philosophical concept that posits the universe's fundamental laws appear finely tuned to allow for the existence of life as we know it. It is divided into two categories: the weak anthropic principle, WAP, which asserts that the observed values of the fundamental constants and quantities of the universe are necessary for carbon-based life, and the strong anthropic principle, SAP, which suggests that the universe must have properties that allow for the emergence of intelligent life. The search for extraterrestrial life and the study of exoplanets have been influenced by the anthropic principle, as it provides a possible explanation for the Fermi paradox and bolsters hopes of finding a world capable of supporting life. The principle also raises questions about the nature of reality, the role of human consciousness, and the potential future of human civilization and the universe itself. Despite its many intriguing implications, the anthropic principle remains a controversial and debated concept. Critics argue that it is not a scientific principle, and that it may be invoked as a last resort explanation for phenomena that are not yet understood. Nevertheless, the anthropic principle continues to inspire fascinating debates and theories, remaining a vital and thought-provoking part of the conversation as our understanding of the universe evolves. Fine-tuning and the constants of nature. The fine-tuning of the universe refers to the precise values of various fundamental constants and quantities that appear to be delicately balanced to allow for the emergence of life. For example, if the strong nuclear force were slightly weaker, protons and neutrons wouldn't bind together to form atomic nuclei, making the existence of atoms beyond hydrogen impossible. If the weak nuclear force were slightly stronger, stars would burn through their nuclear fuel too quickly, preventing the formation of heavy elements necessary for life. These and many other examples illustrate the remarkable fine-tuning of the universe, which the anthropic principle seeks to address. The Copernican principle and the mediocrity principle. The Copernican principle, named after the astronomer Nicolaus Copernicus, asserts that Earth does not occupy a privileged or unique position in the universe. This idea has been extended to the cosmological principle, which suggests that the universe is homogeneous and isotropic, uniform in all directions, on large scales. The mediocrity principle takes this a step further, positing that Earth and humanity are not special or unique in any significant way. The anthropic principle can be seen as a challenge to these ideas, as it suggests that our existence might be the result of the universe's fine-tuning, implying a certain level of uniqueness or specialness. The doomsday argument. The doomsday argument is a probabilistic argument that stems from the anthropic principle and attempts to predict the total number of humans that will ever exist. The argument is based on the assumption that humans are randomly sampled from the set of all humans who will ever exist. Given our current position in human history, The argument suggests that it is unlikely that we would find ourselves in this particular position if the total number of humans were to be much larger than the number that has already existed. This controversial argument has been met with both support and criticism within the scientific community. Simulation hypothesis. The simulation hypothesis, popularized by philosopher Nick Bostrom, posits that reality as we know it might be a computer simulation created by a highly advanced civilization. This idea links to the anthropic principle, as it raises questions about the nature of reality and the role of intelligent life within it. The simulation hypothesis has gained traction in recent years thanks to advancements in artificial intelligence and virtual reality technologies, which have led some to speculate about the feasibility of creating convincing simulated worlds. The anthropic landscape and string theory. The anthropic landscape is a concept that emerges from the multiverse hypothesis and the anthropic principle. It suggests that the collection of universes within the multiverse contains a wide range of possible properties, and our universe is simply one that can sustain intelligent life. String theory, a theoretical framework in particle physics that attempts to unify the fundamental forces and particles in the universe, has been used to support the idea of the anthropic landscape. String theory predicts the existence of a vast number of possible universes, each with its own set of fields and particles, potentially governed by different fundamental constants. The role of the observer in quantum mechanics. The anthropic principle raises questions about the role of the observer in shaping reality, which has parallels with the interpretation of quantum mechanics. In quantum mechanics, the act of observation is thought to play a crucial role in determining the outcome of certain experiments, as illustrated by the famous double-slit experiment. Some interpretations of quantum mechanics, such as the Copenhagen interpretation, suggest that the act of observation collapses the wave function, transforming a system of probabilities into a definite outcome. This idea has led to debates about the nature of reality and the role of human consciousness, which intersect with the questions raised by the anthropic principle. The enigma of consciousness has puzzled philosophers, scientists, and thinkers for centuries. It is the fundamental question of what gives rise to the subjective experience of being aware and experiencing the world. Despite the progress made in neuroscience, psychology, and related fields, the nature of consciousness remains elusive. One intriguing perspective on the enigma of consciousness is the idea of a cosmic connection. This perspective suggests that consciousness is not a product of the brain, but rather a fundamental aspect of the universe, akin to space, time, and matter. This idea is inspired by the panpsychist perspective, which posits that consciousness is a universal property present at all levels of reality. The cosmic connection perspective is supported by the hard problem of consciousness, which argues that subjective experience cannot be fully explained by physical processes alone. The argument goes that while we can understand the neural correlates of consciousness, the subjective aspect of experience, the what it's like to have an experience, remains unexplained. Another argument in favor of the cosmic connection perspective is the inherent subjectivity of consciousness. Consciousness is inherently subjective, and it is challenging to reconcile this subjectivity with the objective nature of the physical world. The cosmic connection perspective offers a solution any system that has integrated information or the ability to process and combine information in a non-trivial way. According to IIT, the amount of consciousness in a system is proportional to the amount of integrated information it has. This theory suggests that consciousness may be present in various systems, from the human brain to the universe itself. As we stand at the precipice of a new era in cosmology, the future of this captivating field promises to unveil a realm of unknowns that will challenge our fundamental understanding of the universe and push the boundaries of human knowledge to unprecedented heights. The quest to unravel the deepest mysteries of the cosmos has been a relentless pursuit, fueled by intellectual curiosity, technological advancements, and a burning desire to comprehend the grand tapestry of existence itself. At the forefront of this cosmic odyssey lie three pivotal frontiers: the quest for a grand unified theory, the advent of cutting-edge observational astronomy, and the rise of quantum computing and simulations. Each of these frontiers holds the potential to revolutionize our understanding of the universe and offer unprecedented insights into the nature of reality itself. Let's begin with the holy grail of theoretical physics, the search for a grand unified theory, DUI. For decades, physicists have been grappling with the fundamental incompatibility between our current theories of quantum mechanics and general relativity. While quantum mechanics governs the realm of the infinitesimally small, describing the behavior of subatomic particles with remarkable precision, general relativity reigns supreme in the domain of the infinitely large, elucidating the nature of gravity and the fabric of spacetime itself. However, these two pillars of modern physics appear to be irreconcilable, leading to a profound disconnect in our understanding of the universe's fundamental building blocks and the forces that govern their interactions. The quest for a grand unified theory aims to bridge this gap, unifying the principles of quantum mechanics and general relativity into a single overarching framework that can explain the behavior of matter, energy, and spacetime across all scales, from the subatomic realm to the vast expanses of the cosmos. Imagine the implications of such a revolutionary theory. It would not only resolve long-standing paradoxes and inconsistencies in our current understanding of physics, but also offer insights into the very nature of reality itself. From the earliest moments of the Big Bang to the ultimate fate of the universe, a grand unified theory could provide a comprehensive and coherent explanation for the fundamental workings of the cosmos, unveiling a deeper layer of reality that has eluded us for centuries. But the future of cosmology is not confined solely to the realms of theoretical physics. The advent of cutting-edge observational astronomy promises to open new windows into the universe, enabling us to peer deeper into the cosmic tapestry and uncover secrets that have remained hidden from our view. At the forefront of this observational revolution is the James Webb Space Telescope, JWST, a marvel of engineering and scientific ingenuity. With its unprecedented sensitivity and resolution, the JWST has the capability to observe the faintest and most distant galaxies, offering a glimpse into the earliest epochs of the universe's formation and evolution. Imagine the excitement of witnessing the birth of the first stars and galaxies mere billions of years after the Big Bang itself. These cosmic relics, long shrouded in the veil of time and distance, could hold the keys to understanding the intricate processes that shaped the universe we inhabit today, shedding light on the formation of the first structures and the distribution of matter and energy in the early universe. But the JWST is just the beginning. The next generation of ground-based telescopes, such as the Extremely Large Telescope, ELT, and the Giant Magellan Telescope, GNT, promise to revolutionize our observational capabilities even further. With their massive collecting areas and advanced instrumentation, these colossal observatories will enable astronomers to study the faintest and most distant objects in the universe with unprecedented detail, unlocking new frontiers in our understanding of galactic evolution, dark matter, and the nature of spacetime itself. Imagine the thrill of detecting the faint ripples of gravitational waves emanating from the mergers of black holes or the collisions of neutron stars, events that have long eluded our direct observation, but hold the potential to reveal the most extreme environments in the universe, where the fabric of spacetime is stretched to its limits. But the future of cosmology extends beyond observational astronomy alone. The advent of quantum computing and advanced simulations promises to revolutionize our ability to model and understand the most complex phenomena in the universe, from the behavior of black holes to the intricate dance of dark matter and dark energy. Quantum computers, harnessing the principles of quantum mechanics, possess the ability to perform calculations and simulations that are simply beyond the capabilities of classical computing systems. Imagine the power of these quantum machines, capable of simulating the evolution of the universe from the earliest moments of the Big Bang, taking into account the intricate interplay of matter, energy, and the fundamental forces that govern their interactions. Such simulations could provide unprecedented insights into the formation and evolution of cosmic structures, the behavior of dark matter and dark energy, and even the ultimate fate of the universe itself. By recreating the most extreme environments and conditions in the virtual realm, cosmologists could explore scenarios that are inaccessible to direct observation, pushing the boundaries of our understanding and potentially unveiling new paradigms of reality. Moreover, the integration of these advanced simulations with observational data from cutting-edge telescopes and observatories could pave the way for a new era of cosmological exploration, where theoretical models and observational evidence converge to paint a comprehensive picture of the universe's origins, evolution, and ultimate destiny. As we stand at the threshold of these groundbreaking frontiers, the future of cosmology is poised to unveil a realm of unknowns that will challenge our fundamental understanding of the universe and push the boundaries of human knowledge to unprecedented heights. The quest to unravel the deepest mysteries of the cosmos has always been a journey of relentless curiosity, intellectual audacity, and a burning desire to comprehend the grand tapestry of existence itself. While the road ahead is paved with challenges and uncertainties, the potential rewards are truly awe-inspiring. The quest for a grand unified theory, should it succeed, would not only resolve long-standing paradoxes and inconsistencies in our current understanding of physics, but also offer insights into the very nature of reality itself. From the earliest moments of the Big Bang to the ultimate fate of the universe, such a theory could provide a comprehensive and coherent explanation for the fundamental workings of the cosmos, unveiling a deeper layer of reality that has eluded us for centuries. The advent of cutting-edge observational astronomy, spearheaded by marvels like the James Webb Space Telescope and the next generation of ground-based observatories, promises to open new windows into the universe, enabling us to peer deeper into the cosmic tapestry and uncover secrets that have remained hidden from our view. Imagine the excitement of witnessing the birth of the first stars and galaxies mere billions of years after the Big Bang itself, or detecting the faint ripples of gravitational waves emanating from the mergers of black holes or the collisions of neutron stars, events that hold the potential to reveal the most extreme environments in the universe, where the fabric of space-time is stretched to its limits. And as we venture into the realms of quantum computing and advanced simulations, we are presented with the unprecedented opportunity to model and understand the most complex phenomena in the universe, from the behavior of black holes to the intricate dance of dark matter and dark energy. These simulations could provide unprecedented insights into the formation and evolution of cosmic structures, the behavior of dark matter and dark energy, and even the ultimate fate of the universe itself, pushing the boundaries of our understanding and potentially unveiling new paradigms of reality. Yet, as we embark on these groundbreaking frontiers, we must also confront the profound philosophical and existential implications that arise from the potential discoveries and revelations that await us. The unveiling of new cosmic truths and the shattering of long-held paradigms will inevitably challenge our perceptions of reality, our place in the universe, and the very foundations of our existence. It is a humbling realization, one that forces us to confront the boundaries of our current understanding and acknowledge that there may be entire realms of existence and modes of being that we have yet to uncover. It is a reminder that the universe is far grander and more complex than we can possibly imagine, and that the pursuit of knowledge is a never-ending journey filled with wonder and awe. The future of cosmology is a tapestry woven from the threads of possibility, and it is up to us, as the inheritors of this cosmic legacy, to continue unraveling its mysteries, one revelation at a time. The quest for a grand unified theory, theory, is one of the most ambitious and intriguing endeavors in the history of physics. The idea of a single overarching framework that reconciles all fundamental forces and phenomena in the universe has captivated scientists and philosophers alike. From ancient Greece to modern-day research, the pursuit of a DUT has been a driving force behind some of the most groundbreaking discoveries in physics. The earliest attempts to unify the fundamental forces date back to the ancient Greeks, who recognized that the natural world was governed by a set of underlying principles. Aristotle, in particular, proposed that the universe was governed by four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. However, it wasn't until the 19th century that the concept of a unified theory began to take shape. In the 19th century, James Clerk Maxwell formulated a set of equations that unified the previously separate theories of electricity and magnetism into a single coherent framework. This breakthrough, known as Maxwell's electromagnetism, demonstrated that a single theory could encompass multiple forces and phenomena. The early 20th century saw the rise of quantum mechanics and relativity, two revolutionary theories that transformed our understanding of the universe. However, these theories were fundamentally incompatible within the framework of classical physics. Quantum mechanics described the behavior of particles at the atomic and subatomic level, while relativity described the behavior of gravity and the large-scale structure of the universe. In the 1960s, physicists Sheldon Glashow, Abdus Salam, and Steven Weinberg developed the electroweak theory, which unified the electromagnetic force and the weak nuclear force. This breakthrough paved the way for the development of the Standard Model of particle physics, which describes the behavior of fundamental particles and forces in the universe. Despite the success of the Standard Model, it is incomplete. It does not account for gravity, dark matter, or dark energy, which are essential components of the universe. The search for a DUT continues, with physicists exploring various approaches, including superstring theory, loop quantum gravity, and causal dynamical triangulation. One of the most promising approaches to a DUT is superstring theory, which posits that the fundamental building blocks of the universe are not particles, but tiny, vibrating strings. These strings give rise to the various particles and forces we observe in the universe. Superstring theory has the potential to unify all fundamental forces, including gravity, within a single framework. Loop quantum gravity, another approach to a GUT, posits that space is quantized, meaning that it is composed of discrete, granular units rather than being continuous. This theory has the potential to reconcile quantum mechanics and general relativity, two theories that are fundamentally incompatible within the framework of classical physics. Causal dynamical triangulation is a quantum gravity theory that uses a discretized spacetime, similar to loop quantum gravity. This theory has the potential to describe the behavior of gravity and the large-scale structure of the universe, while also being compatible with the principles of quantum mechanics. The quest for a grand unified theory is a testament to human curiosity and the boundless potential of the human mind. From ancient Greece to modern-day research, the pursuit of a DUT has driven some of the most groundbreaking discoveries in physics. While the search for a DUT continues, the progress made so far is a testament to the power of human ingenuity and the importance of fundamental research. A DUT has the potential to revolutionize our understanding of the universe, providing a single overarching framework that reconciles all fundamental forces and phenomena. The implications of a DUT are profound, with the potential to unlock new technologies, new sources of energy, and new insights into the nature of reality itself. Ultimately, the quest for a DUT is a reminder of the importance of fundamental research and the boundless potential of the human mind. As we continue to push the boundaries of knowledge, we are reminded of the infinite possibilities that lie before us and the profound impact that a geode could have on our understanding of the universe and our place within it. The modern era of observational astronomy has been marked by tremendous advancements in telescope technology. Ground-based telescopes, like the extremely large telescope, EOT, in Chile, are pushing the limits of optical astronomy with mirrors designed to gather as much light as possible. These telescopes use adaptive optics technology to correct the distortion caused by Earth's atmosphere, allowing for clearer views of the cosmos than ever before. Space telescopes, such as the Hubble Space Telescope and its successor, the James Webb Space Telescope, JWST, have revolutionized our view of the universe. Positioned above Earth's atmosphere, these observatories can capture electromagnetic waves, such as infrared and ultraviolet, that are otherwise absorbed before reaching the planet's surface. The JWST, with its large primary mirror and sensitive instruments, is designed to look further back in time than any other telescope, providing insights into the early universe just after the Big Bang. Radio telescopes, such as the Very Large Array in New Mexico and the upcoming Square Kilometer Array (HSK) project, which will be built in South Africa and Australia, explore the universe at radio wavelengths. These facilities are crucial for studying phenomena like pulsars, black holes, and for the search for extraterrestrial intelligence, SETI. Radio astronomy allows astronomers to detect and analyze objects that are not visible with optical telescopes. Observatories like the IceCube Neutrino Observatory in Antarctica are exploring the universe through particles like neutrinos. These nearly massless particles travel through space undisturbed by magnetic fields or matter, providing information from the cores of stars and from supernova. High-energy astrophysics also includes studying cosmic rays and gamma-ray bursts, which are some of the most energetic events in the universe. Techniques like interferometry, which uses arrays of telescopes to simulate a much larger telescope, have provided unprecedented resolution, allowing astronomers to image surfaces of stars and to map the orbits of exoplanets. Astrometry, the precise measurement of the position and movement of stars, is being revolutionized by missions like Gaia, which is creating the most accurate 3D space catalog ever. The study of exoplanets, planets orbiting stars other than the Sun, has grown tremendously. Missions like Kepler and TSS, Transiting Exoplanet Survey Satellite, have identified thousands of these planets, some of which might be capable of supporting life. Techniques like transit photometry and radial velocity measurements are crucial in these discoveries. In conclusion, observational astronomy is experiencing a golden age. New technologies and methodologies are allowing us to observe the cosmos in ways that were unimaginable just a few decades ago. From ground-based telescopes achieving new levels of clarity to space observatories capturing data across the electromagnetic spectrum, each advancement brings a deeper understanding of our universe. In the ever-evolving world of technology, the advent of quantum computers and simulations has ushered in a new era of scientific discovery and innovation. These revolutionary machines harness the principles of quantum mechanics to process information in ways that classical computers simply cannot, opening up a vast array of possibilities for research and development. Quantum computers operate on the fundamental principles of superposition and entanglement. Superposition allows quantum bits, or qubits, to exist in multiple states simultaneously, enabling quantum computers to perform multiple calculations at once. Entanglement, on the other hand, links qubits together, allowing them to share information instantaneously and with perfect accuracy, even across vast distances. These unique properties of quantum computers have far-reaching implications for a wide range of industries and fields, from cryptography and finance to drug discovery and artificial intelligence. For example, quantum computers can break traditional encryption methods with ease, leading to the development of new, quantum-resistant encryption techniques. In finance, quantum computers can optimize portfolio management and risk assessment, leading to more efficient and profitable investments. In drug discovery, quantum simulations can predict the behavior of molecules and proteins, allowing researchers to design more effective drugs and treatments. One of the most exciting applications of quantum computers is in the field of quantum simulations. These simulations allow scientists to model complex systems and phenomena that are beyond the capabilities of classical computers. For example, quantum simulations can accurately predict the behavior of materials at the atomic and molecular level, leading to the development of new materials with unique properties. They can also simulate chemical reactions and biological processes, providing valuable insights into the mechanisms of life and disease. As quantum computers and simulations continue to advance, their impact on society and industry will only grow. With the ability to process information at unprecedented speeds and with unparalleled accuracy, these machines will revolutionize the way we solve problems, make decisions, and understand the world around us. In the ever-changing landscape of technology, the advent of quantum computers and simulations represents a monumental shift in the way we process information and conduct research. Harnessing the principles of quantum mechanics, these machines offer unparalleled capabilities for solving complex problems and simulating intricate systems, with far-reaching implications for industries ranging from finance and cryptography to drug discovery and artificial intelligence. As quantum computers and simulations continue to advance, their impact on society will only grow, ushering in a new era of scientific discovery and innovation. With the ability to process information at unprecedented speeds and with unparalleled accuracy, these machines promise to revolutionize the way we solve problems, make decisions, and understand the world around us. As we look to the future, the advent of quantum computers and simulations stands as a testament to the boundless potential of human ingenuity and the limitless possibilities that lie ahead. The exploration of the cosmos and the pursuit of unraveling its deepest mysteries is a noble endeavor that has captivated humanity throughout the ages. However, as we venture deeper into the uncharted realms of the universe, we must confront the profound ethical considerations that arise from our quest for knowledge. These considerations transcend the boundaries of scientific inquiry and compel us to navigate the cosmic terrain with a heightened sense of moral responsibility and foresight. One of the most pressing ethical concerns lies in the realm of scientific experimentation and the potential consequences of our actions. As we push the boundaries of our understanding, we must be cognizant of the far-reaching implications our research could have on the delicate balance of the cosmos. The manipulation of fundamental forces, the creation of exotic forms of matter, or the exploration of parallel universes could potentially unleash unforeseen effects that ripple through the fabric of existence itself. It is imperative that we approach these endeavors with the utmost caution, employing rigorous risk assessments and embracing a precautionary principle that prioritizes the preservation of the cosmic order. We must be willing to impose self-imposed limits and ethical guidelines that safeguard the integrity of the universe and ensure that our pursuit of knowledge does not inadvertently lead to catastrophic consequences. Furthermore, the ethical considerations extend beyond the immediate implications of our scientific endeavors and delve into the realm of existential questions about our place in the cosmos. As we unravel the mysteries of the universe, we may encounter evidence that challenges our fundamental beliefs and worldviews, forcing us to confront the very nature of our existence and the meaning we ascribe to it. Should we encounter evidence of intelligent extraterrestrial civilizations, for instance, we must be prepared to navigate the ethical quandaries that arise from such a paradigm-shifting discovery. How would we approach the establishment of interstellar communication and potential interactions? What ethical frameworks would govern our engagement with these advanced civilizations? And how would we reconcile the potential disparities in our respective value systems? Moreover, the exploration of the cosmos may reveal insights into the origins and fate of the universe itself, potentially shedding light on the nature of existence and the fundamental purpose, if any, that underpins reality. Such revelations could profoundly impact our understanding of mortality, consciousness, and the meaning we ascribe to our existence, necessitating a reevaluation of our ethical and philosophical frameworks. Another critical ethical consideration lies in the realm of resource allocation and the prioritization of scientific endeavors. The pursuit of cosmic exploration and the development of cutting-edge technologies require immense financial and intellectual investments, often diverting resources from more immediate societal needs and humanitarian efforts. It is our moral imperative to strike a delicate balance between the pursuit of knowledge and the alleviation of suffering, ensuring that our cosmic aspirations do not come at the expense of neglecting the pressing issues that plague our terrestrial existence. We must engage in open and inclusive dialogues that weigh the potential benefits of cosmic exploration against the urgent needs of our global community, fostering a collective vision that harmonizes our cosmic curiosity with our ethical obligations to humanity. Furthermore, the ethical considerations extend to the responsible dissemination and application of the knowledge we acquire from our cosmic explorations. As we unravel the secrets of the universe, we must be mindful of the potential misuse or weaponization of this knowledge, implementing robust safeguards and ethical frameworks that prevent its exploitation for nefarious purposes. The history of scientific discoveries has taught us that even the most benign insights can be distorted and weaponized, leading to devastating consequences. It is our moral duty to anticipate these risks and implement proactive measures that ensure the responsible stewardship of our cosmic knowledge, promoting its use for the betterment of humanity and the preservation of life in all its forms. Ultimately, the navigation of the cosmic terrain demands a heightened sense of ethical awareness and a willingness to confront the profound implications that arise from our pursuit of knowledge. We must embrace a holistic perspective that considers not only the scientific and technological aspects of our endeavors, but also the broader societal, philosophical, and existential ramifications. It is through the integration of rigorous scientific inquiry with a robust ethical framework that we can truly unlock the full potential of our cosmic explorations, ensuring that our quest for understanding is guided by a steadfast commitment to moral integrity, compassion, and the preservation of the cosmic order. The intersection of science and faith has long been a subject of contemplation and debate, as these two seemingly divergent worldviews have captivated the human mind throughout history. Science, with its empirical methods and evidence-based claims, seeks to unravel the mysteries of the natural world, while faith, rooted in spiritual beliefs and personal experiences, provides a framework for understanding the transcendent and metaphysical aspects of our existence. Despite their apparent disparities, exploring the interplay between science and faith reveals intriguing connections and potential avenues for reconciliation. Science, as we know it today, has its roots in the thirst for knowledge and understanding of the natural world. Through systematic observation, experimentation, and analysis, scientists have deciphered the intricate mechanisms governing the cosmos, from the vastness of the universe to the tiniest particles that make up matter. The scientific method, with its emphasis on objectivity and reproducibility, has propelled humanity's understanding to unprecedented heights, empowering us to make advancements in fields such as medicine, technology, and engineering. Yet, science alone cannot answer the profound questions that lie at the core of human existence. It cannot address questions of purpose, morality, or the existence of a higher power. This is where faith enters the equation. Faith, often grounded in religious or spiritual traditions, provides a lens through which individuals seek meaning and purpose in their lives. It offers a framework for grappling with profound existential questions and provides solace, hope, and guidance in the face of uncertainty. While science and faith may seem at odds, numerous scientists throughout history have seamlessly integrated their scientific pursuits with their personal faith. From Isaac Newton, who saw his scientific discoveries as a testament to the divine order of the universe, to modern scientists like Francis Collins, the former director of the Human Genome Project, who finds harmony between his Christian faith and scientific exploration, there are countless examples of individuals who have navigated the intersection of science and faith. One avenue of reconciliation lies in recognizing the distinct realms to which science and faith belong. Science operates within the realm of the natural world, seeking to understand its laws and mechanisms through empirical observation and experimentation. Faith, on the other hand, operates within the realm of the metaphysical, exploring questions that transcend the boundaries of scientific inquiry. Embracing the complementary nature of these realms allows for a more nuanced understanding of the world, where the pursuit of scientific knowledge can coexist with the exploration of transcendent truths. Moreover, both science and faith share common values and aspirations. Both seek truth, albeit through different methodologies. Both foster a sense of wonder and awe, encouraging us to marvel at the intricacies of the universe and our place within it. Both offer frameworks for ethical and moral guidance, emphasizing the importance of compassion, empathy, and stewardship. In recent years, interdisciplinary fields such as science and religion have emerged, aiming to bridge the apparent gaps between science and faith. Scholars in these fields explore the historical, philosophical, and theological dimensions of the interplay between science and faith, fostering dialogue and mutual understanding. They recognize that science and faith, far from being irreconcilable, can inform and enrich one another, leading to a more holistic understanding of reality. In conclusion, the intersection of science and faith presents a fascinating realm of exploration where seemingly disparate worldviews can find common ground. By recognizing the distinct but complementary realms to which science and faith belong, embracing shared values and aspirations, and fostering interdisciplinary dialogue, we can navigate this intersection with curiosity, humility, and a deeper appreciation for the multifaceted nature of our existence. In doing so, we may uncover new insights, bridge gaps, and reconcile worldviews, expanding our understanding of both the natural and the transcendent aspects of reality. The vast expanse of the cosmos, a tapestry of celestial wonders, captivates the human spirit with its awe-inspiring grandeur. From the infinitesimal dance of subatomic particles to the majestic swirls of galaxies, the universe unveils a symphony of complexity and beauty that transcends the limits of our understanding. Delve into the unfathomable depths of black holes, where the very fabric of space-time becomes distorted, bending light and warping the very essence of reality. Witness the birth of stars, as clouds of gas and dust collapse under the relentless pull of gravity, igniting into brilliant beacons that illuminate the cosmic canvas. Ponder the mysteries of dark matter and dark energy, the elusive components that shape the large-scale structure of the universe, holding galaxies together and driving its ever-accelerating expansion. Gaze upon the myriad of celestial bodies, each a unique testament to the extraordinary processes that govern the cosmos. Explore the dynamic landscapes of the planets, where raging storms, towering mountains, and flowing rivers reveal the intricate interplay of geological and atmospheric forces. Venture beyond the confines of our solar system, delving into the realm of exoplanets, where distant worlds orbiting alien suns challenge our understanding of planetary formation and the potential for extraterrestrial life. The cosmos, a vast and ever-evolving tapestry, invites us to contemplate our place within the grand scheme of existence. From the vast reaches of intergalactic space to the infinitesimal scales of the quantum realm, the universe displays a tapestry of interconnected systems, each a testament to the power of natural laws and the resilience of the cosmic dance. As we gaze upon the celestial wonders, we are humbled by the sheer magnitude of the unknown, propelled to explore, to question, and to unravel the mysteries that lie beyond the horizon of our own understanding. The birth of galaxies can be traced back to the earliest epochs of the universe, mere billions of years after the Big Bang. In those primordial times, the cosmos was a vast, homogeneous expanse of hot, dense plasma, with minute density fluctuations seeded by quantum fluctuations in the fabric of space-time itself. These infinitesimal ripples in the cosmic density field, amplified by the process of inflation, would eventually become the seeds from which the first structures in the universe will emerge. As the universe expanded and cooled, these density fluctuations grew in amplitude, driven by the relentless force of gravity. Matter was drawn towards the denser regions, creating increasingly dense clumps and filaments that would eventually collapse under their own gravitational attraction, giving rise to the first protogalactic clouds. These massive, turbulent clouds of gas and dark matter represented the embryonic stages of galaxy formation, setting the stage for the intricate dance of matter and energy that would shape the cosmic tapestry we observe today. Within these protogalactic clouds, the intricate interplay between gravitational forces, gas dynamics, and the influence of dark matter began to unfold. Dark matter, an elusive and invisible substance that dominates the mass content of the universe, played a crucial role in this process. Its gravitational influence acted as a cosmic scaffolding, providing the gravitational wells within which ordinary baryonic matter could accumulate and condense, forming the first stars and the building blocks of galaxies. The formation of these first stars, known as population IOE stars, marked a pivotal moment in the universe's evolution. These massive, short-lived stars were forged from the pristine hydrogen and helium gas that permeated the early cosmos, initiating a chain of events that would shape the galaxies we observe today. Their intense ultraviolet radiation and powerful stellar winds ionized the surrounding gas, creating the first ionized bubbles in the intergalactic medium, a process known as reionization. As these first stars exhausted their fuel and underwent cataclysmic supernova explosions, they enriched the surrounding environment with heavier elements, seeding the cosmic tapestry with the raw materials necessary for the formation of subsequent generations of stars and the birth of galaxies. These stellar relics, along with the dense cores of gas and dark matter, coalesced under the inexorable force of gravity, forming the first protogalactic disks and the embryonic structures that would eventually evolve into the diverse array of galaxies we observe in the present-day universe. The evolution of these protogalactic structures was driven by a complex interplay of gravitational, hydrodynamic, and radiative processes, each contributing to the intricate tapestry of galactic morphologies we witness today. Spiral galaxies, with their iconic pinwheel shapes and gracefully winding arms, emerged from rotating protogalactic disks. The delicate balance between gravitational forces, angular momentum, and gas dynamics sculpted these majestic structures, with dense molecular clouds condensing into stellar nurseries within the spiral arms, fueling the ongoing cycle of star formation. In contrast, elliptical galaxies took shape through the violent mergers and collisions of smaller protogalactic structures. These cataclysmic events, driven by the gravitational attraction between galaxies and the dissipative effects of gas and dust, reshaped the distribution of matter and energy, creating massive, ellipsoidal structures devoid of the intricate spiral patterns. The intense gravitational forces and shock waves generated during these mergers triggered bursts of star formation and fueled the growth of supermassive black holes at the hearts of these galaxies, shaping their evolution and influencing their ultimate fate. Beyond the realm of individual galaxies, the cosmic dance extended to the grand scale of galaxy clusters and superclusters. These vast assemblages of galaxies, bound together by the immense gravitational pull of dark matter, offered insights into the large-scale structure of the universe and the intricate web of filaments and voids that permeate the cosmic tapestry. The formation and evolution of these cosmic structures were intimately tied to the expansion history of the universe and the interplay between dark matter and dark energy. Dark energy, the mysterious force driving the accelerated expansion of the cosmos, played a crucial role in shaping the growth of structures on the largest scales, influencing the distribution and evolution of galaxy clusters and superclusters. Unraveling the mysteries of galaxy formation and evolution has required a synergistic approach, combining cutting-edge observational techniques, theoretical models, and sophisticated computer simulations. Observational campaigns, such as deep field surveys and spectroscopic studies, have provided invaluable data on the properties and distribution of galaxies across cosmic time, enabling astronomers to reconstruct the evolutionary histories of these celestial cities. Theoretical models, rooted in the principles of gravitational dynamics, hydrodynamics, and particle physics, have offered frameworks for understanding the intricate processes that govern galaxy formation and evolution. From semi-analytical models to state-of-the-art numerical simulations, these theoretical efforts have shed light on the interplay between dark matter, gas dynamics, and the influence of feedback processes such as supernova explosions and the activity of supermassive black holes. Sophisticated computer simulations, powered by cutting-edge computational resources, have brought these theoretical models to life, recreating the intricate tapestry of the cosmic web and the formation and evolution of galaxies with unprecedented detail. These simulations, which incorporate the complex physics of gas dynamics, radiative processes, and the influence of dark matter and dark energy, have enabled cosmologists to explore the parameter space of galaxy formation and evolution, testing hypotheses and refining our understanding of the processes that shape the cosmic landscape. Despite the remarkable progress made in unraveling the mysteries of galaxy formation and evolution, numerous enigmas and unanswered questions remain. The nature of dark matter and dark energy, the role of feedback processes in regulating star formation and galaxy growth, and the influence of environmental factors on galactic evolution continue to be active areas of research, driving the pursuit of new observational facilities and theoretical frameworks. Black holes stand as one of the most fascinating and puzzling phenomena in the cosmos. Initially theorized by John Michell and Pierre-Simon Laplace in the 18th century, and later mathematically described by Carl Schwarzschild using Albert Einstein's equations of general relativity in 1915, black holes have long intrigued scientists and the public alike. These entities are regions in space where the gravitational pull is so intense that nothing, not even light, can escape from them once crossed the threshold known as the event horizon. The discovery of black holes moved from theoretical physics to observational astronomy over the 20th century. The first physical black hole ever identified is Cygnus X1, discovered in 1964 as an X-ray source. Through the study of its X-ray properties and the motion of its companion star, scientists determined that Cygnus X1 must be a black hole. Since then, the study of these cosmic objects has expanded dramatically with the advancement of technology, particularly through the use of space-based telescopes and gravitational wave detectors. Black holes are primarily categorized by their mass and the presence or absence of electric charge and angular momentum. The simplest, known as Schwarzschild black holes, have mass but lack both spin and charge. When a black hole does rotate, it is called a Kerr black hole, exhibiting unique properties such as frame dragging, where the space-time itself is twisted by the spinning of the black hole. Charged rotating black holes are described by the Kerr-Newman metric, although astrophysically, these are considered rare since cosmic objects tend to neutralize their charge. A stellar black hole forms from the gravitational collapse of a massive star at the end of its life cycle, typically possessing up to 20 times the mass of the Sun. When the core of a dying star fails to withstand the gravitational forces, It collapses to a point of infinite density known as a singularity, forming a black hole. On a grander scale, supermassive black holes, which can be millions to billions of times the mass of the Sun, reside at the centers of most large galaxies, including our Milky Way. The origins of these immense structures remain a topic of active research and debate, with theories suggesting they could form through the collapse of a dense star cluster, direct collapse of a massive gas cloud, or the growth of smaller black holes devouring matter and merging. The role of black holes in the architecture of the universe is profound. They influence galaxy formation and evolution through their interactions with their surroundings. The strong gravitational forces of supermassive black holes can regulate the rate of star formation in galaxies, and they are also thought to be the engines behind quasars and other active galactic nuclei, some of the brightest objects in the universe. Powerful jets emitted from the regions near the black hole can inject enormous energy into the surrounding galaxy, impacting its overall structure and evolution. Recent advancements in the study of black holes have been propelled by the detection of gravitational waves, ripples in the fabric of space-time predicted by Einstein, and first observed by the LIGO and Virgo collaborations in 2015. These waves are produced by cataclysmic events such as the mergers of black holes. Observations of these waves provide a new way to study the properties of black holes, including their masses, spins, and the nature of their mergers. Moreover, the Event Horizon Telescope (EHT) collaboration produced the first ever image of a black hole in 2019, specifically of the supermassive black hole in the galaxy M87. This image not only confirmed the existence of black holes' event horizons, but also opened up new avenues for observing and understanding their properties and their immediate environment in unprecedented detail. Understanding black holes continues to challenge our conceptions of physics, particularly at the intersection of quantum mechanics and general relativity. Issues such as the information paradox, where quantum information seems to disappear into a black hole, contradict the principles of quantum mechanics and suggest that new theories may be necessary to fully understand these enigmatic objects. Continued exploration and study of black holes not only deepen our understanding of the cosmos, but also drive advancements in physics, pushing the boundaries of what is known about the most extreme conditions in the universe. As such, black holes are not merely enigmas, they are key to unlocking deeper cosmic secrets. Exoplanets, planets orbiting stars outside our solar system, have been a focus of intense research in recent years, driven by the search for extraterrestrial life. With thousands of exoplanets discovered so far, the possibilities for life beyond Earth have expanded significantly. The quest for life elsewhere in the universe revolves around understanding the conditions necessary for life to emerge and thrive. Habitable zones and stellar properties. A primary factor in determining the potential for life on an exoplanet is its location within the habitable zone, also known as the Goldilocks zone, of its host star. The habitable zone is a region where the temperature is just right for liquid water to exist on the planet's surface. Liquid water is considered essential for life as we know it, as it serves as a solvent, medium for chemical reactions, and a key component of living organisms. The properties of the host star also play a crucial role in assessing an exoplanet's habitability. Stars come in various sizes and temperatures, with different lifetimes and levels of stability. For example, red dwarf stars, which are smaller, cooler, and longer-lived than our Sun, might initially seem like ideal candidates for hosting habitable exoplanets. However, their propensity for powerful stellar flares and the potential for tidal locking of close-orbiting planets can create challenges for the emergence and sustainability of life. Atmospheric composition and climate. The composition of an exoplanet's atmosphere is another critical factor in determining its habitability. A stable atmosphere that can maintain a suitable temperature range and protect the surface from harmful radiation is essential for life. Earth's atmosphere, for instance, contains a mixture of gases, including nitrogen, oxygen, and trace amounts of greenhouse gases like carbon dioxide and methane, which help regulate the planet's temperature through the greenhouse effect. In addition to atmospheric composition, the climate of an exoplanet is crucial in determining its potential to support life. Factors such as the planet's axial tilt, rotation rate, and orbital characteristics can significantly influence its climate. For example, a planet with a high axial tilt might experience extreme seasonal variations, while a planet with a slow rotation rate might have drastic temperature differences between its day and night sides. Geological activity and planetary evolution. Geological activity plays a significant role in shaping a planet's environment and its potential to support life. Plate tectonics, the process by which Earth's crust is broken into plates that move and interact, is thought to be crucial for maintaining a stable climate over geological timescales. This process helps regulate the carbon cycle, which in turn affects the planet's temperature and atmospheric composition. The evolution of a planet over time is also an essential consideration in the search for life. Planetary formation, the development of an atmosphere, and the emergence of life are complex processes that require specific conditions and timeframes. Studying the geological and atmospheric histories of exoplanets can provide valuable insights into their potential to support life. Biosignatures and technosignatures. In the quest for life beyond Earth, scientists are searching for biosignatures, signs of life that can be detected remotely. These can include gases in a planet's atmosphere that are produced by living organisms, such as oxygen or methane, or features on a planet's surface that might indicate the presence of life, like algae blooms or microbial mats. Technosignatures, signs of advanced technological civilizations, are another avenue of investigation in the search for extraterrestrial life. These might include artificial structures, such as satellites or megastructures, and intentional or unintentional signals, like radio transmissions or laser beams. The search for extraterrestrial intelligence, SETI, is an ongoing effort to detect such technosignatures from other civilizations in the universe. Panspermia and the origins of life. The concept of panspermia, the idea that life exists throughout the universe and is distributed by meteoroids, asteroids, comets, or even spacecraft, has important implications for the search for extraterrestrial life. If life can be transferred between celestial bodies, then the potential for life to emerge and evolve on other planets increases significantly. Understanding the origins of life on Earth is also crucial in the search for life beyond our planet. By studying the conditions and processes that led to the emergence of life on Earth, scientists can develop hypotheses about the potential for life to arise elsewhere in the universe. The Fermi paradox and the rarity of intelligent life. The Fermi paradox, the apparent contradiction between the high probability of extraterrestrial life and the lack of contact with such civilizations, raises questions about the rarity of intelligent life in the universe. Possible solutions to the paradox include the rarity of intelligent life, the difficulties in communicating across vast interstellar distances, or the potential for advanced civilizations to self-destruct before making contact with other worlds. The search for life beyond Earth is a complex and multidisciplinary endeavor that involves understanding the conditions necessary for life to emerge and thrive on other planets. By studying exoplanets and their various characteristics, such as habitable zones, atmospheric compositions, and geological activity, scientists are making strides in the quest to uncover the mysteries of life in the universe. The potential for life on other planets, whether in the form of microbial organisms or advanced civilizations, continues to captivate our collective imagination and drive our exploration of the cosmos. The solar system, an in-depth tour. The Sun. The center of our solar system, the Sun is a main sequence star composed primarily of hydrogen and helium. It provides the energy and light that sustain life on Earth. The Sun's immense gravity holds the solar system together, keeping the planets in their respective orbits. Mercury. The smallest and closest planet to the Sun, Mercury has a heavily cratered surface similar to Earth's moon. With a thin atmosphere, known as an exosphere, Mercury experiences extreme temperature fluctuations, from scorching hot during the day to freezing cold at night. Its orbit has a high eccentricity, causing the planet to undergo significant changes in its distance from the Sun. Venus. Venus, the second planet from the Sun, is similar in size to Earth, but has a thick, toxic atmosphere composed primarily of carbon dioxide and sulfuric acid clouds. This dense atmosphere creates a runaway greenhouse effect, resulting in the hottest surface temperatures in the solar system, even hotter than Mercury's. Venus rotates slowly and retrograde, meaning its rotation is opposite to its orbital direction. Earth. The third planet from the Sun, Earth is the only known celestial body to support life. With a diverse geological landscape, a stable atmosphere, and abundant liquid water, Earth provides the ideal conditions for life to thrive. The planet's protective magnetic field, generated by its molten iron core, shields life from harmful solar radiation. The Moon. Earth's natural satellite, the Moon, is thought to have formed from a collision between Earth and a Mars-sized object called Theia. The Moon's gravitational pull creates Earth's tides, and its presence may have played a crucial role in stabilizing Earth's axial tilt, contributing to the planet's relatively stable climate. Mars. Known as the Red Planet, Mars is the fourth planet from the Sun. With a thin atmosphere composed mainly of carbon dioxide, Mars has a cold and dry climate. The planet features the tallest volcano in the solar system, Olympus Mons, and the longest canyon, Valles Marineris. Evidence of ancient water activity on Mars suggests that it may have once been more hospitable to life. Phobos and Deimos. Mars has two small, irregularly shaped moons, Phobos and Deimos, which are thought to be captured asteroids. Phobos, the larger of the two, orbits closer to Mars and is gradually spiraling inward, while Deimos orbits further away. The asteroid belt. Located between Mars and Jupiter, the asteroid belt is a region of space containing millions of rocky and metallic objects, ranging in size from small boulders to dwarf planets like Ceres. The asteroid belt is thought to be the remnants of a planet that failed to form during the early solar system. Jupiter. The fifth planet from the Sun, Jupiter is the largest planet in the solar system. This gas giant is composed primarily of hydrogen and helium, with trace amounts of other elements. Jupiter's Great Red Spot is a massive storm that has been raging on the planet for at least 300 years. The planet has a powerful magnetic field, generating intense radiation belts that trap charged particles. Io, Europa, Ganymede, and Callisto. Jupiter has 79 known moons, with Io, Europa, Ganymede, and Callisto being the most notable. Io is the most volcanically active body in the solar system, with hundreds of active volcanoes. Europa is covered in a thick ice shell, beneath which lies a vast ocean that may harbor life. Ganymede, the largest moon in the solar system, has its own magnetic field and a complex, icy surface. Callisto is heavily cratered and may also possess a subsurface ocean. Saturn. The sixth planet from the Sun, Saturn is a gas giant known for its stunning ring system, composed of ice, rock, and dust particles. Saturn's atmosphere is primarily hydrogen and helium, with traces of other elements. Like Jupiter, Saturn has a strong magnetic field and intense radiation belts. Titan and Enceladus. Saturn has 82 known moons, with Titan and Enceladus being the most significant. Titan, the second largest moon in the solar system, has a thick atmosphere composed of nitrogen and methane, with hydrocarbon lakes on its surface. Enceladus, a small, icy moon, has geysers that erupt water vapor and other materials, suggesting the presence of a subsurface ocean that may support life. Uranus, the seventh planet from the Sun, Uranus is an ice giant composed of water, methane, and ammonia ices, along with hydrogen and helium. Uranus has a unique axial tilt, causing its polar regions to experience extreme seasons, with each pole receiving 42 years of continuous sunlight followed by 42 years of darkness. Neptune. The eighth and farthest known planet from the Sun, Neptune is another ice giant, similar in composition to Uranus. Neptune is known for its deep blue color, which results from the absorption of red light by methane in its atmosphere. The planet has the strongest winds in the solar system, reaching speeds of up to 2,100 kilometers per hour. Triton. Neptune's largest moon, Triton, is a geologically active world with a thin nitrogen atmosphere and cryovolcanic activity. Triton is one of the few moons in the solar system with a retrograde orbit, suggesting it was captured by Neptune's gravity. The Kuiper Belt and Oort cloud. Beyond Neptune lies the Kuiper Belt, a region of icy bodies and dwarf planets, including Pluto, Eris, and Haumea. The Oort cloud, a hypothesized shell of icy bodies, even further from the Sun, is thought to be the source of long-period comets that occasionally visit the inner solar system. In conclusion, our solar system is a diverse and fascinating collection of celestial bodies, each with its unique characteristics and mysteries. From the scorching surface of Venus to the icy moons of Jupiter and Saturn, the solar system offers a wealth of opportunities for scientific exploration and discovery. Stars, the brilliant beacons that illuminate the cosmos, are intrinsically woven into the fabric of the universe's grand tapestry. Their birth, life, and ultimate demise are not mere celestial events, but cosmic narratives that transcend the boundaries of time and space, shaping the very existence of the elements that make up our world, and seeding the cosmic landscape with the raw materials essential for the emergence of life itself. The journey of a star begins in the vast, swirling clouds of gas and dust known as nebulae. These cosmic nurseries, stretching across light years, are the birthplaces of stellar systems, where the interplay between gravity, gas dynamics, and magnetic fields sets the stage for the formation of new stars. Within the dense cores of these nebulae, gravitational instabilities trigger the collapse of massive clouds of hydrogen and helium, initiating a process that will ultimately ignite the nuclear furnaces at the hearts of these celestial bodies. As the cloud collapses under its own gravitational pull, conservation of angular momentum causes it to spin faster, flattening into a rotating disk. This disk, known as an accretion disk, serves as a gravitational funnel, channeling matter onto the central core, where the increasing pressure and temperature set the stage for the ignition of nuclear fusion reactions. The ignition of these nuclear furnaces marks the birth of a new star, a celestial beacon that will shine for billions of years, fusing hydrogen into helium and unleashing immense amounts of energy that radiate outward, illuminating the cosmic tapestry. The delicate balance between the inward pull of gravity and the outward radiation pressure establishes the star's luminosity and temperature, determining its place on the famous Hertzsprung-Russell diagram, the cosmic map that charts the evolutionary paths of stars. As a star burns through its hydrogen fuel, its core contracts, and the outer layers expand, causing the star to become a red giant. In this phase, the star's outer layers are shed, enriching the surrounding interstellar medium with heavier elements forged in the star's nuclear furnace. This process of stellar nucleosynthesis, the fusion of lighter elements into heavier ones, is a fundamental cosmic alchemy that seeds the universe with the building blocks of planets, asteroids, and ultimately, life itself. For stars of moderate mass, the journey ends with the shedding of their outer layers, leaving behind a dense core known as a white dwarf. These stellar remnants, no larger than Earth but with masses comparable to the Sun, are the final resting places of stars like our own, destined to slowly cool and fade into the cosmic backdrop over billions of years. However, for the most massive stars, the journey takes a more cataclysmic turn. As these behemoths exhaust their nuclear fuel, their cores contract under the immense force of gravity, triggering a runaway fusion process that culminates in a spectacular supernova explosion. In these cosmic cataclysms, the star's outer layers are violently ejected into the surrounding space, while the core collapses under its own gravitational pull, forming a neutron star, or, in the most extreme cases, a black hole. These supernova events are not merely celestial fireworks, but cosmic forges that synthesize the heaviest elements in the periodic table, including gold, silver, and uranium. The intense temperatures and pressures within these stellar furnaces allow for the fusion of heavier nuclei, creating elements that could never be forged in the cores of less massive stars. The expanding debris clouds from these supernova, rich in these newly forged elements, seed the interstellar medium with the raw materials necessary for the formation of new stellar systems and planets. This cosmic recycling process ensures that the elements essential for life, forged in the hearts of dying stars, are dispersed throughout the universe, setting the stage for the emergence of worlds like our own. Beyond the creation of heavy elements, supernovae also play a crucial role in shaping the cosmic landscape itself. The powerful shock waves and intense radiation emitted during these cataclysmic events can trigger the collapse of nearby molecular clouds, igniting the birth of new stars and galaxies. Additionally, the kinetic energy released by supernova can influence the dynamics of interstellar gas, shaping the structure and evolution of galaxies, and contributing to the cosmic cycle of matter and energy. The death of stars, whether through the gentle shedding of their outer layers or the violent eruptions of supernova, is not an end but a beginning, a cosmic rebirth that seeds the universe with the raw materials essential for the emergence of new worlds and the perpetuation of the cosmic cycle. This intricate dance of stellar birth, life, and death is a testament to the interconnectedness of all things in the universe, a grand symphony of matter and energy that echoes through the cosmic tapestry, reminding us of our profound connection to the stars that gave birth to the elements that make up our world and our very existence. As we gaze up at the night sky, we are not merely witnessing the twinkling of distant suns, but bearing witness to the cosmic alchemy that has shaped the universe since the dawn of time. Each star is a cosmic crucible, forging the elements that will one day seed the birth of new worlds, and each supernova is a cosmic renaissance, dispersing the seeds of life throughout the vast expanse of the cosmos. Dark matter and dark energy are two of the most elusive and intriguing components of the cosmos, fundamentally shaping our understanding of the universe. Despite their invisibility and the mystery surrounding their nature, these two entities are thought to constitute about 95% of the total mass energy content of the universe. Their discovery and ongoing investigation represent one of the most challenging and exciting areas of modern astrophysics. The concept of dark matter first emerged in the early 20th century. It was astronomer Fritz Zwicky who, in the 1930s, observed that galaxies within the Coma cluster were moving at velocities that implied the presence of much more mass than could be accounted for by the visible matter alone. Zwicky termed this missing mass "dunkle materie," dark matter. This observation was further substantiated by the work of Vera Rubin in the 1970s, who studied the rotation curves of galaxies. Her findings showed that galaxies rotate at such speeds that, without an additional mass, they would tear themselves apart according to the laws of physics as understood at the time. This additional mass, which does not emit or absorb light, was again attributed to dark matter. Dark matter does not interact with electromagnetic forces, which means it does not absorb, reflect, or emit light, making it extremely difficult to detect directly. It primarily interacts through gravity, and its presence is inferred from its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. Various candidates for dark matter have been proposed, including weakly interacting massive particles, WIMPs, axions, and sterile neutrinos, though none of these particles have yet been detected. In contrast, dark energy is a relatively more recent discovery proposed to explain the observed acceleration in the expansion rate of the universe. This phenomenon was discovered in 1998 through observations of distant Type Ia supernova, which served as standard candles for measuring cosmic distances. These observations indicated that the universe's expansion is accelerating, a discovery that contradicted the then prevailing theory that the universe's expansion should be slowing down due to gravitational attraction. Dark energy is even more mysterious than dark matter because it is not only invisible but also does not seem to interact through any of the fundamental forces except gravity. Its nature and mechanisms are unknown, but it is uniformly distributed throughout the universe and exerts a negative pressure, leading to the acceleration of the universe's expansion. The most accepted hypothesis is that dark energy is a property of space itself, as described by the cosmological constant in Albert Einstein's equations of general relativity. Another theory posits the existence of a dynamic energy fluid or field, known as quintessence, which changes over time and space. The existence of dark matter and dark energy raises fundamental questions about the composition of the universe and the laws that govern it. For instance, the lambda-cold dark matter, LCDM, model is currently the favored model for describing the structure of the cosmos. This model incorporates the cosmological constant, which is associated with dark energy, and cold dark matter, CDM, which moves slowly compared to the speed of light. The LCDM model successfully explains many observed features of the universe, including the cosmic microwave background radiation, the distribution of galaxies in clusters and superclusters, and the accelerating expansion of the universe. Nevertheless, numerous experiments and observations are underway to probe the nature of dark matter and dark energy more deeply. These include direct detection experiments for dark matter, such as those conducted in underground laboratories, like the Large Underground Xenon Experiment, LUX, and the future experiments with the Xenon 1T detector. Additionally, dark energy is being studied through observations of galaxy clusters, supernova, and the large-scale structure of the universe, as well as experiments like the Dark Energy Survey, DES, and the upcoming Euclid satellite mission by the European Space Agency. Understanding dark matter and dark energy is not just about comprehending what most of the universe is made of. It also involves unraveling the fundamental physics that governs all of reality, potentially leading to new physics beyond the standard model and a deeper understanding of the cosmos. In the vast expanse of the cosmos, celestial bodies constantly interact with one another, forging a tapestry of cosmic events that are both awe-inspiring and deadly. From the gentle dance of galaxies to the cataclysmic impact of asteroids, these collisions reveal the dynamic and sometimes violent nature of the universe. Galaxy collisions, the dance of titans. Galaxies, vast collections of stars, gas, and dust, are not isolated entities but rather part of an ever-changing cosmic landscape. As galaxies move through space, their paths inevitably cross, leading to some of the most spectacular cosmic events known to us. When two galaxies collide, the sheer force of the interaction can lead to a variety of phenomena. Stars, gas, and dust are torn from their orbits, creating massive shockwaves that ripple through the galaxies. These shockwaves can trigger the formation of new stars, as gas and dust are compressed and heated, leading to the birth of new stellar nurseries. In some cases, galaxies can merge, forming a single more massive galaxy. This process, known as galaxy mergers, can take billions of years and involves the complex interplay of gravity, gas dynamics, and star formation. The resulting galaxy often has a unique structure, with spiral arms, bars, and central bulges that reflect the history of its formation. Asteroid impacts, nature's cosmic hammer. While galaxy collisions are grand on a cosmic scale, asteroid impacts represent a more localized but equally powerful form of celestial interaction. When an asteroid or comet slams into a planet or moon, the resulting explosion can reshape the landscape and alter the course of history. One of the most famous examples of an asteroid impact is the Chicxulub crater, located off the coast of Mexico. This massive impact, which occurred approximately 66 million years ago, is believed to have been the cause of the mass extinction event that wiped out the dinosaurs and many other species. The impact released an enormous amount of energy, equivalent to billions of atomic bombs, and sent debris flying across the planet, triggering wildfires, tsunamis, and a nuclear winter effect that plunged the Earth into darkness and cold for years. Even today, asteroids continue to pose a threat to our planet. NASA and other organizations are actively monitoring near-Earth objects, or NEOs, in an effort to detect and track potentially hazardous asteroids that could collide with Earth in the future. By understanding the dynamics and consequences of asteroid impacts, scientists hope to develop strategies for mitigating the risks and protecting our planet from these cosmic hammers. In the vast and ever-changing universe, cosmic collisions reveal the dynamic and sometimes violent interactions between celestial bodies. From the grand dance of galaxies to the cataclysmic impact of asteroids, these events offer a glimpse into the complex and awe-inspiring nature of the cosmos, reminding us of the power and beauty that lie beyond our world. Imagine standing on the surface of Mars, the red planet, with its rusty-hued landscape stretching out before you. Looking up, you'd see a pinkish sky, the result of fine dust particles suspended in the thin atmosphere, scattering sunlight in a way that gives the sky its distinctive color. The Martian sky would also appear brighter during the day than Earth's sky, due to the lower atmospheric pressure, allowing for a clearer view of the stars. On Titan, Saturn's largest moon, you would find yourself enveloped in a thick orange-brown smog created by the interaction of sunlight with the moon's nitrogen-rich atmosphere and methane clouds. Looking up, you would catch glimpses of Saturn and its rings, along with other moons, through occasional breaks in the haze. The sky would appear darker than on Earth, with the sun appearing as a dim reddish orb. Venus, Earth's sister planet, presents a far less hospitable environment. Standing on the surface, you would be surrounded by thick, yellowish-gray clouds composed of sulfuric acid and other noxious gases. The atmosphere is so dense that you would barely be able to see a few meters in front of you, let alone glimpse the sky above. The sun would appear as a faint, diffuse light, struggling to penetrate the perpetual cloud cover. Io, one of Jupiter's moons, offers a stark and otherworldly landscape. Looking up, you would see Jupiter, an immense, banded sphere dominating the sky. The gas giant's immense gravity causes Io's surface to be constantly reshaped by volcanic activity, resulting in a landscape dotted with active volcanoes and vast lava fields. Io's thin atmosphere, consisting mainly of sulfur dioxide, would give the sky a faint yellowish tint. On Europa, another of Jupiter's moons, you would find yourself on an icy cratered plain, with Jupiter looming large in the sky. The moon's surface is covered by a thick ice shell, beneath which lies a vast ocean that may harbor life. Europa's tenuous atmosphere, composed mostly of oxygen, would give the sky a pale blue hue, with the sun appearing as a small, distant pinprick of light. Standing on the surface of Triton, Neptune's largest moon, you would experience a frigid, nitrogen-rich atmosphere with temperatures well below freezing. Looking up, you would see Neptune as a massive, deep blue orb, surrounded by a system of faint rings. Triton's sky would appear a ghostly blue, with the sun appearing as a distant, dim star. The moon's geysers, erupting plumes of nitrogen gas and ice particles, would contribute to a delicate, transient atmosphere. Uranus, the sideways planet, offers a unique perspective for sky gazing. Due to its extreme axial tilt, one of its poles would be continually bathed in sunlight, while the other would be shrouded in darkness for decades at a time. The sky above would appear in shades of blue, reflecting the planet's methane-rich atmosphere. The sun would appear as a tiny, distant point of light, barely visible against the backdrop of the planet's vast, swirling clouds. Pluto, the dwarf planet, presents a frozen landscape of nitrogen, methane, and carbon monoxide ices. Looking up, you would see a dark, star-filled sky, with the sun appearing as a tiny, distant point of light, no brighter than Venus appears from Earth. Charon, Pluto's largest moon, would dominate the sky, appearing as a large, dark disk against the backdrop of stars. On exoplanet Kepler 186f, a distant world located in the constellation Cygnus, you would find yourself on a rocky, Earth-sized planet orbiting within its star's habitable zone. The sky would be bathed in a deep red hue, as the planet's M-type red dwarf star emits primarily red and infrared light. The sun would appear as a large reddish orb, casting a dim, eerie light across the alien landscape. In conclusion, the skies and landscapes of alien worlds offer a diverse and fascinating array of sights, colors, and atmospheres. From the resty vistas of Mars to the icy realms of Europa and beyond, these distant worlds captivate our imagination and inspire us to explore the cosmos, seeking to uncover the mysteries that lie beyond our own planet. The expanding universe. The expanding universe is a fundamental concept in cosmology, describing how the distance between galaxies is increasing over time. This phenomenon was first proposed by Belgian astronomer Georges Lemaitre in the 1920s, who suggested that the universe is expanding based on Einstein's theory of general relativity. Evidence for the expanding universe came in 1929 when American astronomer Edwin Hubble discovered that the light from distant galaxies exhibits a redshift, meaning that their wavelengths are stretched, making the light appear redder. Hubble interpreted this redshift as a Doppler effect, indicating that galaxies are moving away from us. Furthermore, he found that the further away a galaxy is, the faster it is receding. This relationship, known as Hubble's law, provides strong evidence for the expanding universe theory. The Big Bang theory, proposed by Lemaitre and later developed by other scientists, suggests that the universe began as an infinitely dense and hot singularity around 13.8 billion years ago. The singularity rapidly expanded and cooled, eventually giving rise to the formation of atoms, stars, and galaxies. The ongoing expansion of the universe is a natural consequence of this initial event. The cosmic microwave background, CMB, radiation provides further evidence for the expanding universe and the Big Bang theory. Discovered accidentally by Arno Penzias and Robert Wilson in 1965, the CMB is a faint, uniform glow of microwave radiation that permeates the universe. This radiation is considered the afterglow of the hot, dense state of the early universe, supporting the idea that the universe has been expanding and cooling ever since. In the 1990 observations of distant supernova revealed that the expansion of the universe is not only happening, but also accelerating. This unexpected discovery led to the proposal of dark energy, a mysterious and unseen force that counteracts the gravitational attraction of matter and drives the acceleration of the cosmic expansion. The nature of dark energy remains one of the most significant mysteries in modern cosmology. The future of the cosmos is intimately linked to the universe's expansion. If the current rate of acceleration continues, the universe will eventually become a vast, empty expanse, with galaxies and galaxy clusters drifting further and further apart. Over trillions of years, stars will exhaust their nuclear fuel, leaving behind black holes, neutron stars, and other stellar remnants. Eventually, even these objects may decay, leading to a cold, dark, and virtually empty universe known as the heat death or Big Freeze scenario. Alternatively, if dark energy continues to strengthen, the universe could eventually undergo a catastrophic event known as the Big Rip. In this scenario, the accelerating expansion would become so powerful that it would tear apart galaxies, stars, and even atoms, leaving behind a featureless, empty void. The expanding universe and its implications for the future of the cosmos continue to be a topic of active research and debate among astronomers and cosmologists. As new observations and theories emerge, our understanding of the universe's fate will continue to evolve, providing insights into the fundamental nature of space, time, and the forces that govern the cosmos. The quest to unravel the mysteries of the cosmos has been an enduring pursuit of humanity, fueled by an insatiable curiosity and a burning desire to push the boundaries of our knowledge. In this cosmic odyssey, technological advancements have played a pivotal role, enabling us to transcend the limitations of our terrestrial existence and venture deeper into the vast expanse of the universe. The latest innovations in spacecraft, telescopes, and propulsion systems are redefining the frontiers of space exploration, ushering in a new era of discovery and unveiling realms of the cosmos that were once beyond our reach. At the forefront of this technological revolution are the cutting-edge spacecraft that serve as our emissaries to the celestial unknown. From robotic explorers to crewed missions, these engineering marvels are designed to withstand the harshest conditions of deep space, enduring immense temperature extremes, intense radiation, and the relentless onslaught of micrometeorites. The latest generation of spacecraft boasts advanced shielding systems, robust communication arrays, and sophisticated navigation systems, enabling seamless operations and data transmission across vast interplanetary distances. One of the most remarkable feats of modern spacecraft design is the development of reusable launch vehicles, a game-changing innovation that has significantly reduced the cost and complexity of space missions. Companies like SpaceX, with their groundbreaking Falcon 9 and Falcon Heavy rockets, have ushered in a new era of reusable spaceflight, enabling the recovery and reuse of rocket boosters, thereby slashing launch costs and increasing mission frequency. Beyond Earth orbit, the exploration of our solar system has been propelled by a diverse array of robotic explorers, each tailored to the unique challenges and scientific objectives of their respective targets. The Mars rovers, such as Curiosity and Perseverance, are engineering marvels, equipped with advanced instrumentation, autonomous navigation systems, and sophisticated sampling mechanisms, enabling them to traverse the rugged Martian terrain and unravel the secrets of the red planet's geological history. Venturing further into the outer reaches of our solar system, the spacecraft like New Horizons and Voyager have pushed the boundaries of deep space exploration, providing unprecedented insights into the distant worlds of the Kuiper Belt and the interstellar medium beyond our solar system's heliopause. Complementing these remarkable spacecraft are the cutting-edge telescopes that serve as our windows to the cosmos. Ground-based observatories, such as the Extremely Large Telescope, ELT, and the Giant Magellan Telescope, GMT, are redefining the limits of our observational capabilities. With their massive collecting areas and advanced instrumentation, these colossal observatories will enable astronomers to study the faintest and most distant objects in the universe with unprecedented detail, unlocking new frontiers in our understanding of galactic evolution, dark matter, and the nature of spacetime itself. In the realm of space-based telescopes, The James Webb Space Telescope, JWST, stands as a crowning achievement of modern astronomical engineering. Equipped with cutting-edge infrared imaging and spectroscopic capabilities, the JWST is poised to revolutionize our understanding of the earliest epochs of the universe, peering through the veil of cosmic dust to observe the birth of the first stars and galaxies mere hundreds of millions of years after the Big Bang. Beyond mere observation, the quest for deeper space exploration has also driven advancements in propulsion systems, enabling us to transcend the limitations of conventional chemical rockets and venture farther into the cosmic frontier. The development of ion propulsion systems, which utilize the acceleration of charged particles to generate thrust, has opened new avenues for deep space missions, providing efficient and long-lasting propulsion capabilities for interplanetary and interstellar voyages. Moreover, the pursuit of advanced propulsion technologies, such as nuclear thermal rockets and fusion-based propulsion systems, holds the promise of enabling rapid transit to distant celestial bodies, potentially reducing interplanetary travel times from years to mere months. These cutting-edge propulsion concepts could pave the way for crewed missions to the outer planets and beyond, expanding the horizons of human exploration in ways never before imagined. In addition to these technological marvels, the field of space exploration has also witnessed remarkable advancements in areas such as in-situ resource utilization, ISRU, which aims to harness extraterrestrial resources for the production of propellants, construction materials, and life support systems. By leveraging the resources found on celestial bodies like the Moon, Mars, and asteroids, future space missions could become more self-sustaining and cost-effective, enabling prolonged stays and the establishment of permanent outposts beyond Earth. Furthermore, the integration of artificial intelligence, AI, and machine learning algorithms into space exploration systems has opened new frontiers in autonomous operations, data analysis, and decision-making. Intelligent systems can process vast amounts of data from spacecraft instruments, identifying patterns and anomalies that would be difficult for human analysts to detect. Additionally, AI-powered systems can optimize mission plans, trajectories, and resource allocation, enhancing the efficiency and effectiveness of space exploration endeavors. As we venture deeper into the cosmos, the technological advancements in spacecraft, telescopes, propulsion systems, and related fields are redefining the boundaries of our exploration capabilities. Each new innovation brings us closer to unraveling the profound mysteries that lie at the heart of the universe, unveiling realms of existence that were once beyond our wildest imaginings. The pursuit of these technological marvels is not merely a testament to our scientific and engineering prowess, but a profound expression of the human spirit, a relentless quest to push the boundaries of knowledge, to transcend the limitations of our terrestrial existence, and to embrace the infinite wonders that the cosmos has to offer. With each new discovery, we inch closer to understanding our place in the grand tapestry of the universe, and with each technological breakthrough, we open new doors to the unseen realms that lie just beyond the horizon of our current understanding. The fascination with space has permeated popular culture, influencing a wide array of artistic and narrative mediums, from films and literature to artwork and music, shaping public perceptions and fueling imaginations about the cosmos. This cultural phenomenon can be traced back to early speculative fiction and has evolved with advancements in space exploration and astronomy. In literature, the works of early science fiction authors like H.G. Wells and Jules Verne laid the groundwork for space exploration themes. Wells' The War of the Worlds, and Verne's From the Earth to the Moon not only entertained readers, but also introduced them to the thrilling possibility of extraterrestrial life and space travel, long before the actual landing on the Moon. As the 20th century progressed, authors like Arthur C. Clarke, Isaac Asimov, and Philip K. Dick expanded the genre, infusing their narratives with detailed speculations about the future of humanity and technology, much of which centered around our relationship with space. Films have arguably been the most visually impactful medium through which the majesty of space has been explored and celebrated. Stanley Kubrick's 2001, A Space Odyssey, based on Clarke's writings, stands as a seminal work that combines profound narrative ambition with groundbreaking visual effects, presenting space as both wondrous and menacing. The Star Wars franchise, beginning in 1977, took a more fantastical approach, embedding space within the genre of space opera, filled with epic battles and mythic narratives, thereby appealing to both the sense of adventure and the timeless struggle between good and evil. The space shuttle era and real-life missions also found their echoes in film and TV. Apollo 13, directed by Ron Howard, meticulously chronicled the real-life crisis of the Apollo 13 mission, emphasizing human vulnerability amidst our technological achievements in space. Television series such as Star Trek, which began in the 1960s, offered a utopian vision of future space exploration driven by exploration and diplomacy, impacting generations' views on technology and morality. Art and music have also played significant roles in shaping the cultural narrative around space. Artists like Chesley Bomestel, known for his detailed renderings of planetary bodies, as seen from other planets and moons, created images that predated actual space photography, fueling public interest and enthusiasm for space exploration. In the realm of music, composers like Gustav Holst with the Planet Suite have audibly explored the mythological and astrological significance of celestial bodies in a way that resonates with both classical music aficionados and general audiences. The influence of space on popular culture also extends to the digital age, where video games like Elite Dangerous and Kerbal Space Program allow players to experience the complexities of space travel and exploration in interactive formats, blending entertainment with educational elements. These games not only provide a simulation of spaceflight mechanics, but also embed the player within a narrative and universe that continues to expand their interest in knowledge about space. Moreover, space has influenced fashion, with designers often drawing inspiration from astronauts' suits, equipment, and the futuristic imagery associated with space exploration. This trend is evident in the high-tech, often metallic fabrics and streamlined designs that mimic space gear, reflecting society's fascination with the intersection of technology, future, and the aesthetics of the cosmos. The continuous interplay between advancements in our understanding of space and its representation in culture creates a feedback loop where each influences the other. As telescopes and spacecraft send back new images and data, artists, writers, filmmakers, and game developers draw on these to create works that resonate with the public, thereby not only reflecting current understandings, but also shaping future aspirations in space exploration. This cultural engagement with space not only enriches our popular media, but also plays a crucial role in sustaining public interest and support for scientific research and space exploration initiatives, demonstrating the power of cultural expressions in shaping and reflecting our collective dreams and fears about the vast, uncharted cosmos. Exploration of stars in the universe. Unveiling the secrets of celestial beacons. In the vast expanse of the cosmos, stars stand as beacons of light, guiding our quest to understand the universe. As we venture into the depths of space, we strive to explore and learn from these celestial wonders, seeking to unravel the mysteries of stellar birth, evolution, and death. Stellar birth. Nurturing stars in nebulae. Stars are born from the vast clouds of gas and dust known as nebulae. These cosmic nurseries contain the raw materials necessary for star formation, and as they collapse under their own gravity, they create dense regions where stars begin to take shape. The process of star birth, or stellar nucleosynthesis, involves the fusion of hydrogen atoms in the star's core, releasing vast amounts of energy in the form of light and heat. This energy, in turn, drives powerful stellar winds and radiation that shape the surrounding nebulae, creating intricate patterns and structures that are visible across vast distances. Stellar evolution, the life cycle of stars. Once a star is born, it embarks on a journey through various stages of evolution, each marked by unique characteristics and phenomena. The life cycle of a star is determined by its mass, with more massive stars evolving more rapidly and dramatically than their lower mass counterparts. For low-mass stars, like our Sun, the life cycle begins with a long period of hydrogen fusion in the core, known as the main sequence. As the hydrogen fuel is depleted, the star expands and cools, becoming a red giant. Eventually, the outer layers are ejected, forming a planetary nebula, while the core collapses into a white dwarf, a dense, hot remnant that slowly cools over billions of years. For more massive stars, the life cycle is far more dramatic. These stars fuse heavier elements in their cores, eventually producing iron. When the iron supply is exhausted, the core collapses, triggering a supernova explosion that can outshine entire galaxies. The remnants of this explosion can form a neutron star, or, in the most massive cases, a black hole. Stellar death, the final act of celestial beacons. As stars reach the end of their lives, they undergo a final act that can leave behind some of the most fascinating and enigmatic objects in the universe. Supernova explosions, for example, can create beautiful supernova remnants, which are expanding shells of gas and dust that contain the elements necessary for the formation of new stars and planets. In the case of neutron stars and black holes, these remnants represent the ultimate fate of massive stars, where the forces of gravity have compressed matter to unimaginable densities, creating objects that warp the fabric of space and time itself. In our ongoing exploration of the universe, the study of stars and their life cycles offers a window into the fundamental processes that shape our cosmos. By unraveling the secrets of stellar birth, evolution, and death, we gain a deeper understanding of the universe's origins, its composition, and the forces that govern the celestial wonders that fill our night sky. The no-boundary proposal. Another intriguing hypothesis is the no-boundary proposal put forth by James Hartle and Stephen Hawking. This model suggests that the universe did not have a beginning, as traditionally understood, but rather emerged from a sort of timeless quantum state. According to this proposal, asking what happened before the Big Bang is akin to asking what is north of the North Pole. The question itself might not make sense, as time itself would emerge with the Big Bang and not exist prior to it. The multiverse theory. Some cosmologists speculate that our universe might be part of a much larger multiverse, where universes are continually being created. This idea is often linked with the concept of cosmic inflation, a theory that suggests a rapid expansion of the universe moments after the Big Bang. In some inflationary models, inflation is eternal. It stops in some regions, leading to bubble universes like ours, but continues elsewhere. Thus, the Big Bang may not be the beginning, but rather just a transition from a pre-existing high-energy state in a broader multiverse. Aperiodic and cyclic models. The aperiodic model, derived from string theory, presents an alternative where our universe is one of two three-dimensional worlds on parallel branes. These branes collide periodically in the higher dimensional space, and each collision corresponds to what we perceive as a Big Bang. Thus, the cycle of brane collisions could be eternal, and the Big Bang just one of many cycles in the history of the universe. Quantum cosmological models. Quantum cosmology attempts to describe the universe using a wave function governed by the Wheeler-DeWitt equation. In these models, the universe doesn't have a classical beginning, but is rather a quantum superposition of all possible initial states. The universe, according to these theories, could have tunneled from nothing, where nothing refers to a state devoid of space, time, matter, and energy, into the quantum foam of space-time fluctuations, leading to the Big Bang. Information loss paradox and black holes. Some theoretical physicists, including Stephen Hawking, have also explored the relationship between black holes and the early universe. The information loss paradox in black holes, where information that falls into a black hole seems to disappear, parallels questions about the boundaries of our universe. Resolving these paradoxes might offer clues about the state of the universe before the Big Bang. Each of these theories provides a different framework for understanding what could have existed before the Big Bang. While none have been definitively proven, each contributes to the broader quest of understanding the ultimate origins of our universe. This ongoing investigation combines astrophysics, theoretical physics, and quantum mechanics, pushing the boundaries of how we understand time, space, and existence itself. As technology and theoretical insights progress, our view of the pre-Big Bang universe will likely continue to evolve, potentially altering our conception of the cosmos in profound ways. String theory and pre-Big Bang scenarios. String theory, a framework that posits that the fundamental particles we observe are not point-like dots but rather tiny, vibrating strings, suggests a universe with multiple dimensions beyond the familiar three spatial and one temporal dimensions we experience. In the context of pre-Big Bang cosmology, string theory introduces the idea that what we perceive as the Big Bang could be the result of interactions in a higher dimensional space. For instance, the brain world scenario posits that our universe is a three-dimensional brain that interacts with other brains within a higher dimensional space. If these brains collide, the energy released during this collision could manifest as a Big Bang in each of the brain worlds. This model not only provides a potential scenario for what existed before the Big Bang, but also opens up the possibility that the Big Bang was not a singular event, but one of many throughout a larger multiverse. The role of the Plague epoch in understanding the pre-Big Bang universe. The Plague epoch refers to the earliest period of the universe, up to 10 to 43 seconds after the Big Bang, where current theories of gravity and quantum mechanics are insufficient to describe conditions. Understanding this epoch is crucial for any theory that attempts to describe what came before the Big Bang, because physical conditions during this time are so extreme that conventional physics breaks down. Quantum gravity aims to uncover the nature of space, time, and matter during the Plague epoch by merging quantum mechanics with general relativity. Insights into this era could give clues about the state of the universe before the Big Bang, potentially revealing a pre-existing universe or quantum state from which our own universe sprang. By 1980, our understanding of the universe had been shaped significantly by both theoretical advances and empirical discoveries, culminating in a more nuanced and detailed picture of the cosmos than ever before. The latter half of the 20th century, in particular, marked an era of explosive growth in space exploration and astronomical research, with several key developments defining our knowledge at that time. Cosmology and the Big Bang theory. The Big Bang theory had become widely accepted as the leading explanation for the origin of the universe. By 1980, observations such as the cosmic microwave background radiation, discovered accidentally by Arno Penzias and Robert Wilson in 1965, had provided strong empirical support for this model. This faint background glow, isotropic in nature, is a remnant from the early universe, about 380,000 years after the Big Bang, when photons started to travel freely through space. The discovery and subsequent mapping of this radiation provided critical evidence that the universe had indeed started from a hot, dense state and has been expanding ever since. Galactic structure and distribution. The structure and distribution of galaxies also became better understood by 1980. Observations made through increasingly powerful telescopes showed that galaxies tend to cluster together gravitationally into groups and clusters, ranging from small groups like our local group to massive clusters containing hundreds or even thousands of galaxies. Moreover, the realization that these clusters of galaxies could themselves form superclusters began to hint at a large-scale structure of the universe that appears like a web of filaments, known as the cosmic web. Dark matter. One of the most puzzling discoveries was the nature and existence of dark matter. Although the concept had been around since the 1930s, it was through studies like those of Vera Rubin in the 1970s that the presence of this unseen matter became an unavoidable aspect of cosmology. Rubin's observations of the rotation curves of galaxies showed that the outer regions of galaxies were rotating at the same speed as regions closer to the center, contrary to what would be expected if only visible matter were present. This led to the realization that a substantial amount of non-luminous gravitational matter must be present to account for the observed rotational speeds. Stellar evolution. The life cycles of stars had been charted in detail by 1980. Theories of stellar evolution, nucleosynthesis, and the ultimate fate of stars were well established, explaining how stars form, evolve, and die, depending on their initial mass. This period also saw the development of our understanding of more exotic end states of stellar evolution, such as neutron stars and black holes. Extraterrestrial life. The search for extraterrestrial life had taken a more scientific turn with projects like SETI, Search for Extraterrestrial Intelligence, being established. The use of radio telescopes to listen for signals from potential extraterrestrial civilizations was pursued with a scientific rigor that had not been present in earlier speculative discussions about alien life. Planetary science. The exploration of our solar system had advanced significantly by 1980, driven by missions such as the Voyager probes. These missions sent back detailed images and data from the other planets and their moons for the first time, revealing complex atmospheres, geological histories, and potentially habitable environments, especially on moons like Europa around Jupiter. Inflation theory. Although still in its infancy in 1980, the theory of cosmic inflation began to gain traction. Proposed by Alan Guth in 1980, inflation addressed several puzzles of the Big Bang cosmology, such as the horizon problem and the flatness problem, by positing that the universe underwent an exponential expansion in the first fractions of a second after the Big Bang. By 1980, the foundation had been laid for an explosive growth in our understanding of the universe, driven by technological advancements and theoretical breakthroughs. This period set the stage for the next several decades of cosmological research, which would continue to challenge and refine our understanding of the cosmos. The state of knowledge about the universe by 1980 was not just a culmination of discoveries, but also a springboard for new questions and deeper investigations into the nature of the cosmos. Let's delve further into some other significant aspects of our understanding at that time. Quasars and active galactic nuclei, the influence of cosmic inflation on pre-Big Bang theories. Cosmic inflation, a theory first proposed by Alan Guth in the early 1980s, describes a period of extremely rapid exponential expansion of the universe immediately following the Big Bang. Inflationary theory helps explain several puzzling aspects of the universe, such as its large-scale uniformity and geometric flatness. Some inflationary models suggest that inflation is a never-ending process that sporadically spawns new universes. These models often incorporate the idea of a quantum field responsible for inflation, with fluctuations in this field causing inflation to stop in certain regions, and creating what we perceive as the Big Bang. This ongoing process might imply that what we understand as our universe's beginning is merely one of countless similar events in a much larger cosmic landscape, potentially reshaping the concept of time's beginning. Implications for understanding time and causality. If theories suggesting that the Big Bang is not the absolute beginning, but rather a transitional event in a larger cosmic framework are correct, This profoundly affects our understanding of causality and the nature of time. Traditionally, time is viewed as linear, always moving forward from the past to the future. However, if the Big Bang is just one phase in an ongoing sequence of cosmic events, then our classical understanding of linear time might need revision. Time might be better described in terms of a more complex geometry, possibly without a singular beginning or end, challenging the very notion of causality as we understand it. Experimental and observational prospects. Exploring these theories experimentally presents significant challenges. However, cosmologists continue to devise indirect methods of testing these ideas. Observations of the cosmic microwave background radiation, gravitational waves, and the distribution of galaxies can provide clues about the very early universe. Future observatories and experiments, such as improved gravitational wave detectors and more sensitive cosmic microwave background probes, might be able to detect signatures of phenomena like inflation or brane collisions. Each of these theoretical frameworks not only expands our view of the cosmos, but also pushes the boundaries of known physics, inviting us to rethink fundamental concepts about the universe and our place within it. As we develop better tools for observing the universe and refine our theories, our understanding of what came before the Big Bang will continue to evolve, potentially leading to new insights into the nature of reality itself. The brane world scenario, arising from developments in string theory, offers a radical reinterpretation of our universe's structure and its relationship with potentially numerous other universes within a higher dimensional space. This framework has significant implications for our understanding of the multiverse, cosmology, and fundamental physics. Let's delve into some of these implications in greater detail. Dimensionality and fundamental forces. In the brane world scenario, our familiar four-dimensional universe, 3 spatial dimensions plus time, is embedded in a higher dimensional space. These additional dimensions are not necessarily small or compact, as suggested by other string theory models. Instead, they could be large but inaccessible to us, because the standard model particles, like quarks and electrons, are confined to our 3-dimensional brane, while gravity and, potentially, other forces such as dark matter can propagate in the extra dimensions. This idea could explain why gravity is so much weaker compared to other fundamental forces. It is diluted as it spreads through more dimensions. Cosmological implications. From a cosmological perspective, the brane world model can profoundly affect our understanding of the Big Bang, cosmic inflation, and the ultimate fate of the universe. If our universe is just one of many branes within a higher dimensional space, interactions between branes, such as collisions, could trigger events resembling the Big Bang. This provides a potential mechanism for the beginning of our universe that does not require a singularity, but rather results from a physical process, brane collision. Multiverse and brane interactions. The idea that multiple branes may exist in a higher dimensional space naturally leads to the concept of a multiverse, where each brane represents a different universe with possibly different physical laws. In such a scenario, the fundamental constants and even the laws of physics might vary from one brane to another, depending on the brane's properties and its state in the higher dimensional space. Furthermore, interactions between these branes, such as collisions or near misses, could cause significant events within each brane, such as Big Bangs, periods of rapid inflation, or even the end of a universe. Testing the brane world scenario. One of the most tantalizing aspects of the brane world scenario is its potential testability. If gravity can leak into extra dimensions, or if other dimensions influence our brane via gravitational effects, we might observe anomalies in gravitational behavior at large scales or in high-energy physics experiments. For instance, the behavior of gravity at very short distances might deviate from predictions made by general relativity, potentially observable with precise measurements. Implications for dark matter and dark energy. The brain world scenario also offers intriguing explanations for dark matter and dark energy. If dark matter interacts predominantly through gravitational forces, it could be that dark matter consists of particles that are not confined to our brain, but can move in the additional dimensions. Similarly, the mysterious dark energy driving the accelerated expansion of the universe could be a manifestation of the geometry of the space between brains or the dynamics of our brain within the higher dimensional space. In summary, the brain world scenario enriches our conception of the universe with a complex, interconnected multiverse landscape. It challenges traditional views about the isolation of our universe and opens up new avenues for understanding fundamental phenomena like the Big Bang, gravity, and the nature of dark matter and dark energy. As theoretical and experimental physics progress, the brain world model may provide not only deeper insights into the nature of our universe, but also revolutionary ways of testing the limits of our understanding of space, time, and dimensions. The exploration of theories beyond the Big Bang offers a fascinating glimpse into the potential origins and broader context of our universe. From the intricate frameworks of string theory to the expansive concepts of the multiverse, these theories challenge and expand our understanding in profound ways. Key points covered: string theory and pre-Big Bang scenarios. String theory introduces the idea that fundamental particles are tiny, vibrating strings and suggests our universe could be a product of higher dimensional interactions, such as brain collisions. This potentially recasts the Big Bang as one of many similar events across a larger multiverse. Plague epoch's significance. The Plague epoch, the universe's first incredibly brief moment, is critical in understanding the conditions leading up to and possibly preceding the Big Bang. Insights here could reveal a pre-existing universe or state from which our universe emerged. Implications of cosmic inflation. Cosmic inflation explains the uniformity and flatness of the universe and suggests that our universe's beginning might just be one event in an ongoing cosmic process, hinting at an eternal multiverse. The brain world scenario. This scenario posits that our universe is a three-dimensional brain within a higher dimensional space. Interactions between brains, such as collisions, could explain the origins of the Big Bang, suggesting a cosmos where universes are born from the dynamics of brains in a higher dimensional space. Experimental and observational prospects. While these theories push the boundaries of current technology, future advancements in observational astronomy and particle physics may provide evidence to support or refute these models, particularly through studies of gravitational waves and cosmic microwave background radiation. Broader implications for physics and cosmology. These advanced theories encourage a reevaluation of fundamental concepts such as time, space, and causality. They suggest that our traditional linear understanding of time and singular beginnings may be inadequate to describe the complexities of the cosmos. In conclusion, while our current understanding of the universe starts at the Big Bang, these advanced theories suggest a much richer narrative. They postulate that the Big Bang might just be a transitional phase within an enduring, dynamic multiverse. As we continue to refine our theoretical models and enhance our observational capabilities, our grasp of the universe's true nature will inevitably deepen, potentially unveiling a cosmos far more intricate and interconnected than previously imagined. Thanks for watching.